Streaming, let's start now. If you can see my slides now. Okay. Hello everyone. Welcome to the second day of the SAZERAC-SIP on learning the high-redshift universe. I seamlessly stole some slides from Caroline's introduction talk yesterday to remind everyone about the dedicated Slack channel that we have called hashtag 2022 SIP-ML. We encourage everyone to go there and have active discussion with all the speakers and also among the participants. On the bookmarks for the Slack channel, we have all the important links like the Zoom room link, the Gather Town link. This is our effort to emulate the offline conference environment. So please try it out. We also have the link to the Google Drive, where you can upload your slides after your talk if you want. And we also have the link to the YouTube channel where all the sessions will stay forever, and you can watch them later as well, and then come back and ask your questions in the Slack channel. So this is the schedule for today. Broadly, today we'll learn about simulations and how to analyze these simulations and derive information from them. And aptly, we have Paco to give the overview talk about this topic, and now he'll talk about the role of simulations and machine learning in astrophysics. I'll stop my screen now. Paco, take the
sorry, just a quick remark. Sorry, Francisco. Just before, can the non-speaker turn off the video so that it's not too much? The Zoom-in link is stable also for the one that has low band. Let's say. Thank you.
Okay. Okay, you can start sharing now.
Can you see my screen? Let me see.
Yes.
You can see now.
Yes, and before 5 minutes to the end of before the end, I will give you a shout out. I hope.
Thank you. Okay, so thank you very much, guys, for the invitation. It's of course a pleasure for me. Apologies that I have to miss yesterday program. I was actually flying. So I would like to. I think Caroline would like me to talk about the role of simulation and machine learning in astrophysics these days, and I think this is kind of a very timely for this topic. So this is the outline of the talk. I will first talk about the role of simulations, then later a little bit about the role of deep learning. I have seen that there is a lot of talks about the deep learning, machine learning applied to astrophysics. So I just maybe would like to in this talk maybe kind of make people aware that we have to be also careful with this kind of thing. These things are super powerful and super amazing, but there might be also some kind of what's the word? We have to be careful. That's basically one of the messages that I would like to address. And then finally, I would like to talk about opportunities, something that with really machine learning we can really maybe discover new things. So usually thinking in a cosmologies. So in cosmology we usually try to find what are the constituents and the laws governing our universe. And for this, usually we need theoretical predictions in order to extract the information from cosmological surveys. We have been doing perturbation theory for many years, and still we are doing it, and I think we should do it. But it's becoming a little bit more clear, I think, in the field that as we go to smaller and smaller scales, there is much more cosmological information there. There is really much more that we can learn from the universe when we look at the smaller scales than when we look at larger scales. So that's maybe one of the regimes that I think we need to tackle now in this kind of new era. So the problem here is that usually when you go to smaller scales, first of all, the field itself becomes non-linear. So you will need numerical simulations to make theoretical predictions for this. But on top of this, there are, let's say, processes that can really kind of induce effects that maybe you don't control to first order. So I'm talking about, for instance, astrophysics. So things like supernova feedback or agent feedback. We know that these processes are there, and we know that they will change maybe not only even the internal properties of the galaxies that we're considering, but maybe also the matter distribution or the properties of galaxies nearby. So in cosmology, this is kind of a regime where we usually don't try to go. I mean, we try to avoid a regime where astrophysics dominate. Maybe be a little bit more polemic. I will maybe say that people working on galaxy formation and evolution, maybe they don't maybe also care that much about cosmology. Maybe sometimes people just fix cosmology set to the some fiducial value that we know from Planck, something like that, because maybe you don't expect that the cosmology will play such a big role as these astrophysical processes. So again, being a little bit polemic, I will say that sometimes these are kind of like two different fields where maybe sometimes people don't really talk to each other so much. And either way, I think we need numerical simulations to really address the big problems in cosmology, but also I think we need numerical simulations to study astrophysics. And recently one of the things that we decided to do was to, okay, let's maybe try to put all these things together. Let's not consider just cosmology alone. Let's also work with astrophysics. We don't have to really be in the regime where astrophysics is not relevant. The only way to do this, I believe, one of the best ways is through numerical simulations. And I think one of the important things, at least from this decade, is going to be the play of machine learning or deep learning. So, when you combine cosmology with astrophysics, machine learning, and simulations, this is basically what we come out recently with this CAMLS project. So CAMLS stands for Cosmology and Astrophysics with Machine Learning Simulation. It's a suite of more than 4,000 cosmological simulations. Half of them are traditional embodied, so nothing really in particular. The other half are state-of-the-art magneto-hydrodynamical simulations. As we will see later, this is very important. The hydrodynamical simulation has been run with two completely different codes that solve the hydrodynamical equation in two completely different ways. So on one hand, we have the Epoch code, and on the other hand, we have the Gizmo. And as many of you, of course, know, in cosmological hydrodynamical simulation, we are not really able to resolve the scales where many astrophysical processes happen, like the formation of a star, the explosion of let's say, supernova, or feedback from supermassive black holes. So these kind of processes are things that we model in a phenomenological way. And this is what we call the subgrid models. So in our simulation, basically, we have also two completely different subgrid physics. On one hand, we have the illustrious TNG code model, and on the other hand, we have the SIMBA. So these are two state-of-the-art. I will not say that one is better over the other. Ideally, what you would like to do is to make theoretical prediction where, at the end of the day, you don't really rely on one model. Usually, reality will probably not be in agreement with any of these two. When you look at very, 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 very detailed, I will say. So you want to make theoretical predictions that are not model dependent, I will say. So the idea of this was basically, let's explore the parameter space. So what we have here are in a 6-dimensional parameter space. We have two cosmological parameters, omega matter and seed byte, which might be for many applications the most relevant ones. And then we have 4 astrophysical parameters that we believe are maybe the most important ones in order to their impact on cosmological observables. So 2 of them control basically the energy released by supernova feedback. The other 2 control the energy released by agent feedback. So the idea is that you have this 6-dimensional parameter space, And of course, you would like to sample this. You would like to, in principle, make a theory prediction for how these summary statistics, or even how this entire field will look like for this particular point in parameter space. As you can imagine, this is completely impossible to do, right? You cannot really run an infinite number of simulations, or for this very computationally expensive simulation, you cannot really run a simulation every time that you need a point in parameter space. So the main idea of CAMLs was, let's run some simulation, the bigger number that we can. And then, let's use machine learning to basically interpolate in this parameter space in such a way that we can basically cover, in principle, the 6-dimensional parameter space, not only for summary statistics, but also at the field itself. And this will be great, right? Because at that point, you will be able to have a theoretical prediction for every point that you have in parameter space as a function of cosmology and as a function of astrophysics. And if you are interested, for instance, in cosmology, what you would like to do is to marginalize over the astrophysical parameters. But if you are, for instance, more interested in doing astrophysics or study, for instance, the high-redshift universe, maybe you want to marginalize over cosmology. Or maybe you want to learn the relation between cosmology and astrophysics for these fields. So very quickly, before maybe showing the movies that is more interesting, as I say, we have like two completely different suites. We have the Illustrious CNG suite and the Simba suite. And every suite has a lot of different sets. So, for instance, we have the Latin Hypercube set, where we have like 1,000 different simulations with different cosmologies, astrophysics, but also random seed. And something that is important here is that we vary in all these simulations the value of the cosmological parameters within a very, very broad range. I will say really crazy. For instance, for omega matter, we go from 0.1 to 0.5. And we do exactly the same thing for these astrophysical parameters. So in CAMLs, there is a lot of hydrodynamical simulations where galaxies don't really look at all like the real galaxies, right? These are galaxies that might be supermassive, or agent feedback is so strong that everything is blown, all the gas is blown out. But that's perfectly fine, because usually one of the problems that you have when you use neural networks is that neural networks, they tend to learn the priors of the distribution. So if you tell a neural network that this is kind of the universes that you consider, the neural network will learn that there is kind of nothing outside this in general, right? I mean, there might be some ways around this, but in general, this is what happens. So you don't want to be sensitive to the priors that you put. And that's basically what, you just put a very broad prior, and, usually your theoretical prediction will not be affected by these priors. Let me show you maybe the movie. It's a little bit maybe more visual in order to see this. So what I'm going to show you in this movie is the distribution of gas from one of these simulations. And what we're going to be happening is that we're going to change the value of one of these parameters at a time. So let's start. This is, for a simulation with omega matter, it's like 0.1. You can see the large scale structure. Now we have moved to 0.3. You can see that the cosmic web has changed quite a bit. Now we're moving to 0.5, and now we are going to go back to 0.1. And you can clearly see that, the value of omega matter really changed, the distribution of gas in the universe. Not surprising. We're now seeing the same thing for sigma 8. There is an effect. You can clearly, I think you can clearly see it. It's a little bit more subtle, but it really affects, for instance, the abundance of the most massive halos. Now we are considering one of these supernova parameters. And what you can see is that this supernova parameter is becoming larger. There is more gas in the let's say, in the environment of the big halos, but also the small halos are affected by this. Basically, you kind of suppress the whole gas that is on small halos. We are now seeing the same effect for AGN. There is an effect, but this effect is a little bit more subtle, usually only happening in the most massive halos, that are the halos that contains maybe the AGNs. So on small halos, for instance, the effect might be a little bit smaller or might not even be there. This is another of these parameters, supernova 2. And you can see that, for instance, there is clearly a big difference here. And I think finally we are in one of these AGN parameters, the second one. Also, there is an effect. It's a little bit, sometimes subtle to see, but the effect is there. So all these things really change the distribution of gas. And it doesn't matter if we are looking at this like a low redshift, maybe a high redshift agent feedback might not be so efficient, but supernova might really be. And there might be other processes. So at the end of the day, in principle, we would like to really vary all these parameters because, who knows where nature is, or who knows even if this simulation might not even be representative of what reality it is. Let me just show you another movie. I think this is playing. Okay, no. So this is basically a flying through to one of our simulation, and this is as time evolves. You can see, of course, the cosmic web, the density perturbation and becoming larger and larger. You can see the formation of halos, of filaments. And at some point, you will see some kind of explosions. And these are, of course, no feedback or agent feedback. You can see here. I'm not sure if the connection is good enough for maybe you guys to see this properly, but and this kind of shows how complex in general these things are and how the interplay between the different cosmological and astrophysical parameters. So we are zooming out here, and you can see that there are really, each of these guys is kind of a different simulation. So we have like thousands of them, and I believe this is kind of a good way to. Okay, so I have talked about the role of simulation. I have tried to say that I think it's very important to really use numerical simulation and to use the best simulation that one can afford. Now let me talk about the role of deep learning. So I have seen that just from the title that there is a lot of people using deep learning to constrain different astrophysical properties about the universe, the high redshift, the epoch of Reionization and these things. I would like to mention here one particular examples where we have, I think, done a very similar work as many other people will show, but actually the message might be a little bit more negative than what we would like. So let me explain. So what you can see here, these are gas temperature maps. These are, a redshift 0. We could have done this at higher redshift, but I think for illustration should be fine. Every of these maps it only covers an area of 25 by 25 megaparsec, and every map has 256 by 256 pixels. So the resolution is 100 kiloparsec. These are very high resolution maps, and the area is tiny for cosmological standards. Every map has a different cosmology, a different astrophysics, and also a different random set. It's coming from a simulation with a completely different random set. So what we did here was to say, can we do cosmology with this? Can we, instead of using summary statistics, can we train a CNN to try to identify patterns in the cosmic web as traced by gas, in this case, gas temperature, and to see if we are able to constrain cosmology and at the same time to marginalize over astrophysics. So, it's I would say, a relatively simple exercise to do, and of course, it works. So let me, for instance, show you here one panel. This is for omega matter. So, for instance, consider this point here. This point is a map, a gas temperature map, a redshift 0. It's coming from a cosmology of where the value of omega matter is like 0.24. You put this map into a neural network that has been trained, has never seen this map before, and the neural network will give you this. Basically, we compute the posterior mean and the posterior standard deviation without assuming anything about the posterior, so doing likelihood-free inference. And you can see that it produces this value. So the closer that you are to this black line, the better. You can see that you are able to get the value of omega matter with a few % accuracy. This is at the same time that you are marginalizing over baryonic effects at the field level, which is really something very, very nice, I would say. And you can do the same thing for, for sigma 8 or even these astrophysical parameters. We did this for, many other different fields that we have in this simulation. So, gas density, dark matter density, stellar mass. Maybe something that is important is that we did also for H1. That might be very interesting for many of you. And, for all cases, it really works. And maybe I would like to go quickly through it. For instance, for H1, what we find is that beyond the dark matter field and the total matter density field, that these are fields that are you expect to be less affected by baryonic effects, neutral hydrogen was actually the best field to constrain cosmology, not the best field to constrain astrophysics. To constrain astrophysics, either the gas metallicity or this super weird quantity that we consider the magnesium over the hydrogen are the best one. But in terms of cosmology, it's doing a very, very good job. So I think this is, these are maps, are redshift 0, but it's a very nice result for 21 centimeter intensity mapping. But this is maybe the most important thing that I would like to emphasize here. And again, usually I'm very positive, but here I think it's important to kind of address what could be the limitation of this method. We're basically doing likelihood free inference at the level of the field, extracting cosmology and marginalizing all baryonic effects at the field level. This is, it's a bit weird that I said it, but this is really amazing, right? This is really great. This is kind of the dream for a cosmologist. But is this model that the neural network has learned robust? Can we really apply now this model to observation from real data? The answer is no. And the answer is, and the reason is the following. So we trained this neural network using maps from Illustrious TNG, a state-of-the-art hydrodynamical simulation with some model to implement supernova feedback, AN feedback. We marginalize over this. But then once you have this model, can you input into this network one map from, for instance, these SIMBA simulations? As I said before, these SIMBA are also state-of-the-art hydrodynamical simulations, has a completely different way to model supernova feedback, AN feedback. But if I have marginalized over this, hopefully I will expect that this will not, that my neural network will be able to work even with these fields. But it doesn't. So for instance, let me show you here this panel. This is the result that you get for omega matter, where you use a neural network that has been trained using Illustrious TNG, but you test the network using SIMBA. It doesn't work. It fails dramatically, I will say. So we cannot really use this with real data as of today. We don't know why this is happening. It might be that even if in CAMOS we vary everything in a crazy range, and even if we expect that we have marginalized over astrophysical effects, it might be that the simulations still live in different regions in parameter space, and they don't really overlap. This could be a possibility. The second possibility is that maybe the neural network has been learning some numerical artifacts, something that is really unique to Illustrious TNG that it doesn't happen on SIMBA. So let me show you one movie to try to show you maybe why the two things might be living in different points in parameter space. So what you can see in this movie is the very same simulation on the left, run with Illustrious TNG, on the right, run with SIMBA, saying initial random seed. And you can see that for the dark matter field, that is, these things are very similar. This is for the gas density, also very similar. But look at the gas temperature. The differences are striking, right? I mean, they are too large. So it might simply be that, simulations don't really overlap in some high dimensional, when you maybe consider things at the level of the field. And, something that as a community, we need to, I think, worry is that maybe simulation will never be perfect. I wish they will, but, maybe nature and reality is much more complex than the things that we are doing, in 2022. What will happen in this case? How can we deal with these kind of approaches where we really try to do the optimal solution using simulation? We really rely on simulations when we try to do these things. So I think there are some ways around this, but this is, one of the messages that I would like to mention in this talk, that these things are super powerful, but we need to be, we have to be cautious about this. Okay, and very last part about this, I will just like to mention that all these images, we have even 3D grids There are hundreds of thousands of them at different redshift. Everything is publicly available. This is the Commons multi-field dataset. There are more than 70 terabytes of data. I think this is really a beautiful dataset if you are working on these particular things, or maybe if you have a student who want to do a project on cosmology and astrophysics and also want to use deep learning and don't want to train, use the traditional machine learning datasets. This is something like purely, I will say, astrophysical from our community. So it might be good. Maybe one quick thing about this. This is another example of things that we did. Sometimes, we're with real data, we're going to need to deal with mass, or sometimes, for cosmological service, there is a star here, so we need to mask this region. For 21 centimeter. Maybe sometimes you want to mask out the regions where the foregrounds are too large. So, what happened with these kind of things? I mean, are you willing to just mask out this region? So another thing that might be very useful for deep learning is maybe to kind of do this in painting. So for instance, imagine that you have a field like this, and these regions in white are things that you have masked out because there was some problem or the foregrounds are too large, blah, blah, blah. Can you recover what is really in these regions? Because, you might want to take a look at this, or you want to extract information that is on there. So this is a work that we did with Faisan, where we use one of these state-of-the-art in painted method from the machine learning I will say, part. And what we show is that this method works very well even when we have very complex and very state-of-the-art fields, like the one that we're considering here. And on top of this, you can do this even independently of cosmology and astrophysics. You can train your model on some of these and automatically will work with all the others. So, this might be something interesting for the future. I will maybe skip this paper that we did with Sultan and very briefly talk about opportunities. So I would like to mention something that might be of interest for some of you here or might not. But the point that I would like to emphasize is that there is really a lot of opportunities with deep learning. If we have numerical simulation, even if you have real data, of really maybe discovering things, new things, or maybe not, maybe discovering some artifact in the simulations. So this is a work that we did with Caroline, and we basically what we claim is that we can do cosmology with one single galaxy. This is a kind of a big claim, and if true, this will be important or interesting. And if this is not true, then it will be something that we need to, again, worry even more about numerical simulations. So let me explain what we did. So consider that we have one of our hydrodynamical simulations, like these camels. And by the way, I forgot to say all these camels, everything is publicly available. There are more than 4,000 simulations. Everything is publicly available, hundreds of terabytes of data. We even provide some computational resources, so you don't have to even download all the data to your cluster. Maybe not everybody has these resources. So yeah, feel free to check it out. So consider, thank you. So consider one of these boxes that we have in campus. So this simulation has some particular value for the cosmology, for gamma transit mate, and also some particular values for the astrophysics. And you can consider other simulation or other. So at the end of the day, what we do is to consider 800 of these simulations. Every simulation will have a different cosmology. Every simulation will have a different random seed and also a different astrophysics. And in this simulation, there are galaxies. There are dwarf galaxies, there are massive galaxies, there are red galaxies, blue galaxies, there is all kinds of galaxies. So what we do is to consider one single galaxy from these simulations. One single. And then for this galaxy, we consider different internal properties. Like for instance, the gas mass of the galaxy, the stellar mass, the black hole mass, maybe the total mass, in this case, considering also the subhalo where the galaxy is embedded, and many other different properties. And then what we did was to train a very simple neural network, a fully connected layer network, where basically we take these 17 properties and we try to predict the value of omega matter, the error on omega matter, sigma 8, the error on sigma 8, and the same thing for these astrophysical parameters. So you train the network using just one galaxy at a time. And when the network is trained, you test it. So for instance, you consider one simulation. This simulation has been completely researched. So all the galaxies in this simulation, the network has never seen them. And then you consider one particular galaxy from this simulation. And you put into the network and see if this gives you something meaningful or you have wasted your time. So this is what we get. So this is for omega matter. So let me explain. Consider this point here. This point here represents a single galaxy where the value of omega matter, the true value of omega matter from the simulation where this comes from is like 0.32. You take the 17 properties from this galaxy, you put it into a neural network, and the neural network will give you this standard mean, posterior mean, standard deviation of the posterior. And the same thing as before, the closest that you are to this black line, the better. You can see that this works, which is very surprising because this is just like one single galaxy. And yeah, I mean, according to this, it works. We did the same thing for other parameters. You know, for sigma 8, we cannot really say anything about sigma 8. There is no constraining power. And we did the same thing for the astrophysical parameters. So only for this supernova parameter 1, you can say something, but it's not really a lot of information. What we did was also to basically check that this does not happen for some particular galaxies. Basically, what we find is that this holds for all galaxies. So, you know, you take any random galaxy from your simulation, and this method somehow is going to work, surprisingly. This is what I'm showing here. I'm going to just maybe skip because I only have like 30 seconds. So I can talk more in detail, but basically what we find is that galaxy properties live in a manifold. This is our explanation. And this manifold, we believe that is very sensitive to dark matter, to the value of omega matter. So basically what we believe that is going on here is that as you change the value of omega matter, there will be more or less dark matter in the universe, and there will be more or less dark matter in galaxies. And this will really change galaxy properties in a way that is very different to what supernova feedback or AN feedback will do. That's our explanation, and let me just conclude. So I think we really need numerical simulations to study the nonlinear regime or even the regime where is dominated by astrophysics. I think deep learning is very powerful, really amazing powerful, but we need to worry about this robustness and how much can we trust simulations. And I think there is a lot of opportunities for machine learning in the right now. So I will stop here. Thank you, and apologies for the delay.
So much, Paco, for a very nice overview. Questions. We already have some questions on Slack, but if you can, but if the people can want to repeat them here, they can. First of all, Chris, you want to ask your question here?
Yeah, I can do quickly. Yeah, thanks for the talk, Paco. So I just had a question about this intersim test. So this illustrious trained model applied to SIMBA. I was wondering, way of kind of evaluating whether this is a numerical artifact might be to just reduce the resolution of the maps. So you're essentially starving the network of some information.
That's a good question. So the resolution is exactly the same in the two cases. Even the numerical simulation we run, is both of them are 25 megaparsec and they contain 256 cube. Even I think maybe we even probably match the softening that, on smaller scales might be important. So in that sense, yeah. But there might be some other numerical artifact, maybe, I don't know, there is maybe something unique in Illustrious CNG about how they change the temperature on very small scales, something that is not really present on SIMBA. So yeah, unfortunately I cannot maybe give you, but thank you. It's a very good question.
Thanks.
Now, Daniel, do you want to ask?
Yes, can you hear me?
Yes.
Hey, Francisco, very good talk.
Hi, Daniel.
First, one comment about the very beginning, what you said. I fully agree with that approach, that especially if we are doing simulation of galaxy formation at very high redshift, the epoch of Reionization, we are dealing about galaxies living in very massive halos that are high sigma peaks, so they're very sensitive to the cosmology, to a small variation in omega matter, for example. And then my question is about that mismatch between the TNG and the SIMBA when you marginalize over the different between the astrophysics. But when you are talking about the parameter A that you marginalize, is the parameter A the same, the same meaning in TNG and in SIMBA? I mean, that doesn't mean the same for both simulations. It's somehow difficult because they are very different subgroup models.
So thank you, Daniel. Yeah, I of course agree with you. So for the first part, I mean, definitely. I mean, maybe there are things that maybe a high redshift like agent feedback might not be important, but maybe there are other things. I don't know. I mean, sometimes I'm not really an expert on this, but sometimes people say, you know, maybe the metallicity can change things a lot. So regarding this, your question, exactly. So thank you. It's a very good question. So the meaning of these A parameters is not really the same in both simulations. And the reason for this is because the subgrid physics, the subgrid model is different. So we try to match them as close as possible, but sometimes it's really impossible. So you are completely right. But you know, it's always maybe like how are we gonna do this with real data? Because in our subgrid models, maybe this is not really what reality is doing. So, you know, ideally you would like to marginalize over these kind of things, even if, you know, they don't really match among simulations and these kind of things. But they don't match, that's the answer too. Thank you.
Thanks. So guys, now we have to move on. Please ask your other questions on Slack, and Paco, it would be very nice if you can answer them there.
Definitely. Thank you, guys.
Already many more questions there on Slack. Now we go to all the contributed talks. Now all the talks will be for 15 minutes, and for the speakers, they can we recommend to use like 12 minutes and leave 3 minutes for questions, but you can always use the entire 15 minutes and answer the questions on in Slack. So first, Mosima will talk about accelerating Reionization simulations and deriving optimal summary statistics with autoencoders. Mosima, you can start sharing the screen. Yes, we can see your slides. You can start.
Can you see my screen?
Yes, we can see your screen.
Oh, okay,
you can
thank
start
you.
now. I'll give a warning 5 minutes before the end.
Okay, thank you. Hello, everyone. My name is Mosima Masipa. I'm a second-year master student at the University of the Western Cape. Firstly, I would like to thank the organizers of this conference for giving me the platform to share my work with you. So I'm currently working on accelerating Re-Ionization simulations and deriving optical summary statistics using autoencoders. We know that semi-numerical models are the leading candidates when it comes to evolving Re-Ionization. So unlike hydrodynamic simulations, they are very computationally effective and fast because they combine numerical techniques and analytical techniques to evolve the 3D intensity map of the 21 centimeter line during the epoch of reionization. So here I just have like a brief summary of how the semi-numerical model works. So firstly, we start by generating a density field at a redshift of 0. And then we evolve those density fields to other redshifts. And then we collapse the density fields to generate the dark halo matter. And depending on the sources that we're working with whether we are working with AGNs or galaxies, we do photon count, and then we generate the ionization bubbles. So our work here is we are trying to speed up this process of simulating this intensity map. So we want to move from density field straight to the ionized bubbles without first generating the dark halo matter and doing the photon count. So so the motivation behind this is we know that when it comes to parameter recovery, it can be tricky to use the semi-numerical models. So with our project, we are going to be using an autoencoder to move from the density field to the ionization field. So basically, an autoencoder is a neural network that is used to learn data representation efficiently. So an autoencoder consists of 3 parts: the encoder, which compresses and encodes the input data to produce a code known as the latent space. And from the latent space, we're able to reconstruct the inputted image. So our work here was inspired by the work that was done by Chadin et al. In their 2019 paper, whereby they used both the density fields and the sources as the input into their encoder to generate the code. And from the code, they decoded to get the ionization times. So instead of using both the density fields and the sources for our autoencoder, we are using only the density field and feed it into the encoder and then decode it to get the ionized bubbles. So the way in which we went about doing this is we simulated our data using SimFast21, a semi-numerical model, whereby we simulated both the density fields and their corresponding ionization fields. And we splitted this, the data set contained 60,000 images, whereby we splitted them into 80% training set and 20% testing set. So to construct the autoencoder, we used HERA's tuner to find optical parameters for our autoencoder. And we found out that from the autoencoder, the best performing autoencoder from our HERA's tuner was an autoencoder that consisted of 3 layers in the encoder and 3 layers in the decoder. So here we have the loss evolution from our autoencoder. So so basically what the loss evolution does, it shows you how good your model is at predicting the original field. So we ran the autoencoder for about 200 epochs, whereby we realized that as soon as we get somewhere around 20 epochs, the model starts to convert. So the fact that our model is not underfitting or overfitting, it gives us hope that this model can work, even though we can see that the loss in both the training and the validation set is almost 50%. So here here are examples of some of our images that we had in our testing set. So here we have the original field from the SimFast 21 that we generated using SimFast 21. And here we had the reconstructed field from our autoencoder. So I just chose random images from the testing set to show you how our autoencoder is doing in terms of recovering the ionization field. So I didn't follow any specific pattern, I just chose randomly. So since we can't evaluate like all the images in our testing set individually, we decided to plot the power spectrum to show how like the model is doing over the whole sample. So here, so we collected all the power spectra over the testing set for both the original ionization field and the reconstructed ionization field. And in red here, we did the mean of the power spectra. And in the shaded red, we have the difference between this mean and the standard deviation for the original ionization field. And in blue, we did the same thing for the reconstructed ionization field. So at larger scales, we were able to notice that our autoencoder, to some extent, can recover the power spectra. But when we go to the small scale, it is underestimated by a factor of 2. So I'll just give the summary of what I just talked about and the future work. So we designed an autoencoder that takes in the density field and outputs the ionization field. So when we were compiling our model, so in autoencoders, usually what you do is you map your training set, your X to your X, like you map the density field to the density field because you want to be, like you want to reconstruct the same field, but with our autoencoder, we were mapping the density field to the ionization field because that's what we were trying to do. So to speed up this process of reconstructing the ionization field from the density field, we used dense layers instead of convolutional layers. So for the second part of this work, which is to derive optical summary statistics, it's still a work in process also. We are going to explore the latent space. So we haven't explored our code thoroughly, so we're still going to do that. And we want to improve the accuracy of the autoencoder because we, as we've already seen from the loss evolution, our autoencoder is not performing efficiently. So we are going to use this autoencoder on AGN simulations. So the data that we had, that we simulated using SimFast was just the data from like the density fields and the ionization fields from just the galaxies. Thank you.
So much. Questions for Musima? Maybe as people think, I wanted to quickly ask one question. So it was not clear to me. So your input is the density field, and how do you also provide the astrophysical parameters, or is it just one simulation type?
So we haven't really explored this project. We're just testing to see if we can just use the simplest autoencoder to generate, to reconstruct ionization fields. So we are still going to condition our autoencoder to see if we can constrain some parameters. So this is just the simplest autoencoder that we have. I don't know if I've answered your question.
I understand. Yeah.
Okay.
So in the future, you are going to include that more parameters.
I have a question, sorry, but as a co-host, I don't know how to raise the hand. So it was
Yeah,
very
ahead,
interesting
Michele.
talk, Mosima. I wanted to ask you, are you looking at these as inputs? Are you using the say density distribution at a specific redshift or a different?
Yeah, so it's just experimental at the moment, right? So we just generated a random data set. So at different redshift, we didn't focus on like a specific redshift. So yeah, hopefully we can, I don't know, we're still exploring, see how it goes.
Okay. And
Yeah.
do you know, do you have the, how to say, global reionization fraction of your predicted and true map, more or less how much it is? Do you know that? Or?
Yeah, I forgot to quote it. So with this one, so it was like 80% ionized. So it was like, yeah, 0.2 neutral hydrogen. With this one, it was 60% ionized. So 0.4 neutral hydrogen.
Yeah. And did you notice if there is a difference? Let's say 60% ionized is performing better or worse or vice versa?
I didn't really like explore this further because I was just like I just started out with this project. So, but it seems like with the images that I've done, I didn't show them here. So it's like when we go to the extreme, when we have like highly ionized field, the autoencoder doesn't do a good job, like a decent job in reconstructing this field. But there's a certain range whereby it's sort of does like a decent job. So I couldn't find so I was just selecting those images randomly. So I thought maybe if I show maybe 20% ionized, like the bubbles were like small. So I wanted something that would be,
yeah,
you know,
and it makes sense with what you just said. From the power spectra, you see that
yeah,
a small scale you don't.
Yeah, you don't really like it underestimates the power. So
okay, yeah, very interesting. Thank you. Looking forward to see some more results in the future. Cheers.
thank you.
There are a few more questions in Slack. It will be very nice if you can answer them on Slack directly. And you can move on to the next talk. Now we'll hear from Chris Lovell about testing hydro simulations in a new regime by learning the galaxy halo relations at high redshift. Chris, you can.
Great. Yeah. Can you hear me okay?
Start. Yes. And you can see your screen also.
Okay, cool. So yeah, thanks very much.
Is the Zoom floating heads? Can you minimize that?
How do I do that? Hide video panel? No.
Yeah, it won't.
That's gone now. Yeah. Okay.
Yes.
Okay. So I can't see anybody now. So if you need to get hold of me, shout. Yeah, thanks very much. So I'm going to talk a little bit today about using machine learning, this galaxy halo relationship and how this can be used to test hydro simulations in a new kind of regime. I'll talk a little bit about high redshift applications for this at the end, but this will unfortunately be mostly at lower redshift. I apologize. So kind of a goal of galaxy evolution modeling is to simulate a representative population of galaxies, ideally those that we see in the real universe, and resolve all of the relevant physics at all of the required scales. And this requires very large volumes to capture a range of environments, requires high resolution in terms of spatial mass and time, and requires all of the kind of required physics, so things like hydrodynamics and magnetic fields. Now, unfortunately, hitting all three of these things simultaneously is not computationally feasible, so we must make compromises. So one of the ways of doing this is to kind of simplify the physics that we're incorporating into these simulations. So there's a number of phenomenological models, semi-analytic models, for example, that simplify the physics, allowing you to run things at reasonably high resolution and large volumes. If we want to do the physics explicitly, we need kind of fully hydrodynamic models, which often include things like magnetic fields and cosmic rays. And these then come with various resolutions. So there's two main approaches to doing these hydro simulations. You can take a periodic box, so it's essentially a cube with periodic boundary conditions, and then the density within that cube is essentially the mean density of the universe. There's a number of flagship models for this that we've already heard about. Two of these from Paco, so Illustris and Simba. There's also Eagle. These typically have a side length of around 100 megaparsecs, and each gas element has around a mass of 10 to the 6 solar masses. So this is already a couple of orders of magnitude higher than the typical kind of star cluster mass regime. And because of the size of the box, they only typically contain around 10 low mass clusters, nothing in the 10 to the 15 M solar range. However, they do have a nice continuous matter distribution, so it's easy to calculate things like galaxy stellar mass functions and clustering statistics. But because of the small volume, you don't get these massive clusters, and it's also then difficult to build light cones from these things. So an alternative approach is to run what are called zoom simulations. So you essentially take some region of interest selected from a usually lower resolution parent box. You re-simulate this at high resolution with hydrodynamics in your region of interest, and then there's dark matter kind of at lower resolution outside that region. And this has been used to target a number of different objects. So you can target individual galaxies, which has been done with the fire simulations, which is at the top there. You can also target overdense environments such as galaxy clusters. This has been done with the Cluster Eagle project. And you can also, rather than just targeting these overdense extreme environments, you can also target a range of different environments. So we did this in the flares simulations recently. So this selects overdense and underdense environments. So this allows us to capture these extreme environments, but unfortunately, you don't get your continuous matter distribution. So you can't measure things like the clustering statistics, and it's a little bit trickier to measure these kind of composite distribution functions. So the question is, can we combine these two things together to kind of get the best of both worlds? What we want is large volume, continuous matter distribution, enabling us to build these very large light cones, but based on these high resolution simulations, including all of this relevant physics. So in a paper that just accepted recently, we did this with the Eagle simulations and the Sea Eagle simulations. So these are Eagle periodic boxes and Cluster Eagle cluster re-simulations zooms. Essentially what we do is we train a machine to learn the galaxy halo relationship and then apply this to a much larger dark matter only volume to produce this kind of continuous galaxy distribution over a much larger volume than you'd be able to achieve with a single periodic box. So we used, as I said, the periodic Eagle simulation and the zooms together. We actually match between dark matter only and full hydro versions of these simulations. So we take subhalos from both, run on the same initial conditions and match them together. So we then avoid baryonic effects on halos essentially, which allows us to then take our trained model and apply it to a completely new dark matter only box. So this is just showing some of the match statistics, and we have approximately 400,000 halos in these combined regions. So once we've matched these together, our features then are taken from the dark matter simulation, things like the total subhalo mass, circular velocity, the actual group mass of the friends of friends parent. And then what we're predicting are 6 baryonic properties: stellar mass, the total gas mass, star formation rate, etc. And we use a reasonably simple machine learning model. This is an ensemble decision tree method called extremely randomized trees. And we essentially provide all of the subhalo properties directly to this. So this is what some of the results sort of look like. So we have each of our baryonic predictors here, showing the true value on the x-axis against the predicted. You can see for most of these properties, there's a reasonably strong correlation, which is good, which means our machine is able to predict this just from the halo properties. And on the right here, we've got these violin plots, which also show that we're actually matching the overall distribution of these properties as well, not just the one-to-one correlation. So things like stellar mass and stellar velocity dispersion are actually really, really well reproduced. These kind of offsets here are just objects that essentially had 0 gas mass in the simulation and then reasonably unconstrained actually in some of these properties. So it just explains this kind of odd feature. So once we did this, what we could then do is take this trained model apply it to a much larger dark matter only volume. So we chose the P-millennium simulation, essentially is run with the same kind of substructure finder as the EAGLE simulations, but it's 800 megaparsecs on a side. So this is, 8 cubes times larger than the fiducial EAGLE volume, essentially. And so the plot on the left here is showing, you can see the orange line here is the galaxy stellar mass function from the original EAGLE simulation. And the blue line on the right here is our prediction using our trained model. So you can see we're able to extend out to this kind of BCG mass regime. And we're predicting those masses for hundreds of BCGs from hundreds of clusters in this volume, whereas in the EAGLE volume, you've only got, say, 1 or 2 of these objects. So not only can we extend these distribution functions in terms of their dynamic range, we can also measure clustering over much larger scales and up to much higher masses as well, just because we have the statistics now. So this is essentially showing this projected correlation function. The blue line here is EAGLE, and then the orange line is our prediction on this much larger volume. Each of these bins is showing a bin in stellar mass. And essentially with EAGLE, you're only able to measure this up to kind of around 7 or 8 megaparsec scales, simply due to the size of the box. Whereas with our P-millennium, with the machine learning run on it, we can extend this out to much larger scales. And also we've got much larger population of these very high mass or high stellar mass galaxies to measure these statistics on as well. And here's just a number of other distribution functions that we're able to reproduce reasonably well with this machine learning model. So out of the machine, we actually get a number of things which tell us the feature importance. So ERT essentially, just based on where the features lie in terms of the decision trees that make up the ensemble, you get a reasonably good handle on this feature importance. So these plots all show this in various different ways. I'll focus on the one in the middle here to begin with. So this is just a map of the feature importance for each of our baryonic predictors on the x-axis and each of our features on the y-axis. So you can see for most of these, it's Vmax, which actually contributes the most to the prediction for that property. Things like the gas mass, for example, are actually more dependent on the radius, the half mass radius. And the star formation rate as well, for example, is also slightly dependent on this. So we actually tested incorporating a number of other features that encoded the larger scale overdensity, so on various different scales, 1, 2, 4, and 8 megaparsec radii. But we found this didn't actually contribute much to the predictive accuracy. So it's actually, in this case, it's the halo features that dominate and provide the most, contribute the most to the prediction. So moving on to the high Z stuff now. So this is all done at redshift 0.1 using this EAGLE and cluster EAGLE combined training set. So if we want to extend this to high Z, we need more simulations that are run at these high redshifts, and ideally targeting both over and under dense environments. So one of the drawbacks to the approach that we used previously was that we only targeted clusters and these kind of periodic boxes. So the very underdense regions, for example, weren't part of the training set and may produce incorrect predictions. So ideally for this, we've actually got the flare simulations. So I mentioned these previously. This is a series of, hello?
5 minutes.
5 minutes, thank you. So this is a series of Zoom simulations of a range of overdensities targeting the epoch of reionization, so redshifts 5 and above, all using the EAGLE code. We can combine these using, understanding of the actual overdensities they're selected from to produce composite distribution functions. But in this ML framework, it actually provides an ideal training set for this kind of machine learning approach. So this is an example of what we can do just using and understanding the overdensities. So this is the galaxy stellar mass function on the left side, showing that we're able to fully probe the kind of turnover of the mass function out to redshifts of 10, for example. And these two plots here are showing the UV luminosity function and showing that we're able to probe these very, very bright galaxies that we're going to detect in the Euclid wide and Roman surveys that are soon to be coming up. So what we'd like to do ideally is to create these kind of large mock light cones to actually directly compare these observational surveys with the simulations. So this is the Euclid kind of flagship mock light cone, which has an incredibly large volume, but is using quite simple phenomenological models to do this kind of galaxy mapping. So the idea with this approach is that we can take the Eagle hydro simulation, which has all of this detailed physics, and apply this directly to this light cone approach. So this is currently a work in progress, I'm afraid. I hope we'll have some results to show you very, very soon. Some of the things we're actually incorporating here is some improvements on the previous approach are to include these historical halo features, so things such as the assembly and formation time, which will hopefully improve the predictions. This is using merger graphs by Will Roper. We're also going to directly predict the multi-wavelength emission. So by running SCIRT on all of our flares galaxies, as well as the periodic galaxies, we'll have UV to sub-millimeter emission that we can directly hopefully predict from the halo properties. And we're going to apply this to a much, much larger parent DMO box, so around 3 gigaparsec cubes sort of size. And this will enable us to make these incredibly large light cones that will hopefully be of value to these observational surveys. So like I said, this is all kind of work in progress. So if anybody has ideas or comments or questions or wants to get involved, then please give me a shout. Thanks very much.
There's some time for questions. Maybe I'll start with one. So for high redshift in your training set, do you have a population 3 stars, like molecular cool stars?
No, we don't. So this is still using just the kind of base Eagle model. So in terms of population 3 stars aren't fully resolved in this at this kind of resolution. I think for this kind of mass resolution, that would be still quite difficult. However, we found in the flares kind of results so far that we were able to match things like the galaxy stellar mass function, star formation rate functions, and star forming sequence up to redshift 5 to redshift 10 reasonably well. So at least in that regime, the predictions are reasonably good, but for lower mass galaxies and at slightly higher redshifts, I think you need slightly more detailed modeling. But that's just encouragement for people who are perhaps running these kind of high resolution simulations, that this sort of approach may be one way of being able to test it in this large volume regime.
Dan, do you want to ask a question? Garrett?
Yeah, I have some background noise, so I don't know. But anyway, so how will you include reionization in your flares simulations?
So we don't explicitly include reionization in the flares simulations at the moment. It just uses a kind of instantaneous reionization model. Again, this is using the kind of base Eagle model just to kind of test this model in this high redshift regime. But of course, being able to include that would be desirable and be interesting to see how that affects the results that we've had so far. But I don't think that would make a huge impact to the framework we propose here. So it would just impact the individual galaxy properties that we would then be able to train on and apply to these larger volumes.
An interesting aspect there is that if you do zoom ins on different environments, you would expect a low density environment to have a low reionization redshift and a high density environment to have a high reionization redshift. So your instantaneous reionization could be different for different environments.
Yes, absolutely. And there's also a question there about the best way to incorporate that kind of large scale reionization topology in this Zoom environment, and how you include that. But yes, it will obviously make a much larger difference, and this kind of thing you might be able to only probe using this Zoom approach as well.
Yeah, does that answer the question? Okay, let's move on to the next speaker. Thank you, Chris. So now we have Kinjin. Kinjin An will talk about probing the early history of reionization by cosmic variance limited CMB experiments. So Kinjin, we can see your slides. You can start.
All right, thank you. Okay, where's the pointer? Oh, well. Okay, so I will not talk about the machine learning, but I will talk about the new science or the new data you might want to look at in the future. So I'm Kyung-Jin An from Chosun University, and this is based on the work with Hina Sakamoto, Kiyotomo Ichiki, and Kenji Hasegawa in Nagoya, and my student Hyunjin Moon. And thanks for giving me the slot. So a brief recap of the old work and the recent work of mine is a story of pop-3 stars in mini halos. Here you see this color plot on the left column here. This is the simulation that has all the types of halos, mini halos to atomic cooling halos. And on the right, you see only the simulation without the mini halos and only including the atomic cooling halos. And then the stark difference lies in a very high redshift, as you see at redshift 15 or so. And on the right, you see that how the Reionization histories differ in terms of redshift and the ionization fraction. Do you see my pointer?
Yes, yes.
Mouse pointer? Okay, thank you. So, so that was based on the simulation, but to study a larger parameter space, you always benefit from something like Wonson model. So, in last year, with Paul Shapiro and I cooked up the Wonson model. You know, you can see these models something like in the work from Forlanetto 2006, for example. But anyway, the change of the volume fraction has the sink term and the source term and the sink term. The source term being ionization rate, and then which will be proportional to the star formation rate, and they can either be proportional to the change of the collapse fraction of halos, or just can be proportional to the collapse fraction. And the sink term will be recombination rate. So we tested, we tried like 3 different categories in sequential complexity, the vanilla model, something like the old model by Forlanetto, without any feedback. Then it is just the ionization fraction being proportional to the collapse fraction, or the change of the collapse fraction. And then you see that this is the reionization history in terms of redshift and ionized fraction. And then they are quite monotonic, and they are not too much feature in there. Then you can make it a little more complicated by adding rather medium the feedback, which can be the Jeans mass filtering of the medium mass halos when they are put inside the H2 bubbles. Then the star formation may be quenched. If you do that, then you see a little more complexity in the history. Then finally, you can have like vanilla, chocolate, and strawberry model. So we call it self-regulated type 2. And here we focus on the mini halos as well here. And then we suppress the mini halos by Jeans mass filtering and also by the Lyman-Warner feedback. And then you see this at the high redshift, you see the increase of the ionized fraction slowly, and then there is some time for recombination, and then shoots up by atomic cooling halos. So that's a very peculiar feature of this model category. And let's talk about the Cmb polarization. The Cmb polarization, if to make the Cmb polarized, then in the view of the electron must see the equal weighted photon intensities at opposite directions, and also this high intensity region and low intensity region of CMB should be 90 degrees apart. And the only multiple that has that is the quadruple. So you can see the Wayne-Hughes illustration is in here, and you can just flip them and overlay them to make it more clear. But anyway, so this gives you a good parameter, the good old parameter, the CMB optical depth. Basically, it measures how much electron you have. So if you have a different reionization histories, then the optical depth will be different. And there has been over the past years, there has been a tendency for decreasing tau. So starting from WMAP value, something like 0.09. In 2015, when Planck compiled the low frequency instrument data, then they got something like 0.08. And then with the addition of a high frequency instrument as well, the value got down to something like 0.05 or 0.055. So it is tempting to say that the first stars are very late bloomers, and then the reionization happens late because the late reionization translates to the low optical depth. But I will say that please be patient. And the reason why is this. Okay, so let's go to the Miranda et al. 2017 paper. So they analyzed the CMB, Planck 2015 data with the PCA. And then what they got was that, well, we see some hint for the very high redshift reionization at a substantial level. So they said that our 2012 model was kind of favored. But then with the addition of HFI, the Planck team put a very strong constraint on the high redshift ionization. So let's now focus on this new optical depth, tau 15. Let's call it tau 15. So this is the optical depth from redshift 15 and beyond, and then just up to when the reionization begins, okay? And this tau 15 was set by the Miranda to be less than 0.07 at 2 sigma, but the Planck team, with their legacy data, they put a very strong constraint, like 0.007 at 2 sigma. And so far, we only have the upper bound, so that there is no lower bound. And there has been some interesting change of the story. So, so the Planck is here. And when we ourselves analyzed a few models of ours, we found out that the model with high redshift ionization, something like this, which violates the Planck 2020 analysis, was actually a very good fit to the Planck data. So we were very confused. And then Wu et al. And Heinrich and Hu, they said that, well, there seems to be something wrong with the Planck estimate. And then finally, the Planck team put out their erratum, boosting up the tau 15 back to something like 0.018. So our model with a high redshift, strong, high redshift ionization is still very viable. And so I teamed up with the Nagoya team to see how something like LIGHTBIRD, which is the cosmic variance limited CMB experiment, which will launch in 2027, will do to measure this interesting parameter tau 15. And we tested PCA and Harza and smooth method and flex knot methods. So what they differ is that the PCA just does the principal component analysis based on the E mode polarization anisotropy. HS17 is and FlexNet. These actually sample reionization histories directly from the redshift Z and XE plane like this. The difference is that HS17 does only up and down change of the knots, and then later they just connect knots to make reionization histories. FlexNet does, they move points all around and then connect those dots to make up reionization history. And for the PCA seems to do well in terms of discriminating large high-redshift ionization tail models from the tailless models. Basically, tailless and tail means that the reionization exists or does not exist at high redshift. So these the bluish ones here are this well separated from the tailless ones here. So at they can be discriminated at around 2 sigma also. And but the trouble we found was like this. When we did the usual temperature and E mode polarization analysis on our mock data, so this dotted vertical line is our input model for tau 15, but the tau 15 estimate was the black one here, and it was quite far from our input. So we thought about a way to do it better, okay? And then doing it better, we tried to resample the same CMB data on the E mode with a limited L. And the idea is that if you see the K. Ahn and Shapiro 2021, then the tailed reionization models are well separated from the tailless ones at the, if you look at the E mode polarization, at the range of L from 15 to something like 25. So we didn't want to confuse our likelihood from the low multiple, E mode polarization, but just use this one. And then when you do that, then when you do that like this, then the value actually can nicely capture the input value like this. But the story is not that simple. You see that there is certainly a trend when you do that resampling to capture the input value correctly, but it all differs from across the methods, and we tested many different models. So like when you do the resampling, then without resampling from the TTTE and EE analysis, these are the estimates compared to the model, which is a dotted line. And when you do the EE only with the this resampling, then they can be a little bit boosted. But this is all over the place at the moment. So the bottom line is that the cosmic variance limited experiments will come. It is truly ideal. And the good thing is that the tau 15 can be measured with the double wing feature in posterior. So it is not just the upper bound. But the bad thing is that the accurate estimation is still a little bit elusive. So we have to find a better way to do, the accurate estimation of tau 15. Okay, let me stop here. Thank you.
We have one. We may have time for one question for Kenjin, if there is any. I'll ask you one. So in your model 3, you have just one assumption for your POP3 stars or low mass halos, right? Or do you vary many parameters?
So we change the Lyman-Warner threshold over which the mini halos are also pressed in terms of star formation. So we change that parameter, and then also we change, what's the mass of the POP3 stars inside the mini halo. So those are like the main parameters, and also we change the escape fractions. So there are many parameters actually.
You can continue the discussion in Slack. Now we will move on to the flash talk. Benjamin, can you stop? Thank you. Thank you for the talk. I hope all the speakers for the flash talk are ready. I hope the slides are visible now.
Yes. Yes.
Okay. So first, it's Sikar Mittal.
So should I begin?
Yes, you can begin.
Yeah. Okay.
And tell me when you want me to change the slide.
Yeah. Sure. Okay. So I would like to introduce my work on the background of radio photons from the primordial black holes. Please change the slide. Hi, Sambit, change the slide, please.
Yes.
Okay, thanks. Yeah, so the motivation for this work is the Aegis 21 centimeter signal, which, as you all know, has an absorption feature which is more than double than even the most optimistic standard model predictions. So one of the potential explanations of this signal is an excess radio background, which was seen by RK2 in 2011 and was also later independently confirmed by LWA1 in 2018. So this excess radio background in itself is an interesting topic and has been studied several times previously in the last 2-3 years. And so as you can see that this excess radio background, which is the second term in my first equation, is highly non-thermal because of its frequency dependence. So this would then supplement the CMB temperature, and this would enhance the 21 centimeter signal, which I have denoted here by delta dB. So I Sambit, change the slide, please. So there have been several mechanisms that have been proposed as the mechanism for producing this excess radio background, such as the conversion of dark photons into standard model photons, or the annihilation of axion-lug particles into, again, the standard model photons. So in this work, we are going to consider primordial black holes as the originator of this excess radio background. So why primordial black holes? Because they are interesting dark matter candidates, and we have studied it in detail in our previous work. So for this work, we have considered two types of PVH. One first type are the evaporating ultralight PVH. So the special property of this ultralight black hole is that it evaporates, or in other words, it radiates energy and mass due to Hawking emission. However, the Hawking emission for these black holes peaks near mega electronic volt scales. However, we are interested in micro electron volt energies. So we find that the radio emission is highly suppressed and is extremely negligible. So these black holes are clearly ruled out. So we consider an alternative possibility, which are the accreting primordial black holes. So these black holes have the potential to generate strong radio emission. The picture on the right hand side is an artistic impression showing the jets and the where central black hole sitting at the center is typically of the mass 10 to the 8 solar mass. So one important point that I would like to draw attention to is
The synchrotron emission mechanism, which is thought to be the most probable mechanism of generating this radio background, gives rise to a radio brightness temperature in frequency, which follows a power law in frequency and has an index of -2.6. So this -2.6 is also same as the one seen by the Arcade and LWA. So this makes these accreting primordial black holes an interesting and well motivated candidates for producing the excess radio background, and hence also explain the edges 21 centimeter signal. So for more details, I would encourage the audience to check out the paper given at the bottom. So that is all I had to say, and thank you.
Prakash?
Yeah, so I'm Prakash Gaikwad. I'm a postdoctoral fellow at Max Planck Institute of Heidelberg. So our aim in this work was to measure the thermal state of the intergalactic medium between redshift range 5 and 6. For this, we have performed observations of 5 quasar spectra, which are for all of them are at high redshift greater than 6.1. They all have a high resolution, like 6 kilometers per second, and very high signal to noise ratio. In the top figure, you can see that these are the spectra, the observed spectra that we have carried out using different kind of telescopes like Mike and HIRIS. We simulate or we model these transmission spikes that you see in this observation spectrum and also in the simulations. We use 2 kinds of simulations. One is optically thin simulations in which there is a uniform UV background, and the other one is a 2 radiative transverse simulations. The bottom panel shows the difference between the homogeneous reionization model, which is optically thin, and the other one using the patchy reionization model. Next, please. Next slide. Yeah. So if you look at the transmission spikes in the top panel, the observed transmission spikes, you can see there is a structure in it. If you look at the simulation, we have seen that if we increase the temperature of the intergalactic medium, the spike widths actually increases, that is, they are broadened. So we use this phenomena called the spike width distribution function to measure the temperature of the intergalactic medium. In the bottom panel, what we are showing is the result of this analysis. So we measure 2 parameters, which is the normalization and slope of the temperature density relation. And the error bars that are shown over here are accounts for observational and modeling uncertainty, for example, continuum fitting uncertainty or any other uncertainty. So the main result of our work was that it favors a late reionization model for both hydrogen as well as helium. I did not talk about helium, but we use 100 different quasar absorption spectra for helium reionization. So this is the final result that I want to take from this talk. Thank you very much.
Patty?
Hi, so I'm Patty Bullen. I'm a graduate student at UC Davis, working with Marisha Badach and Brian Lameau, looking at galaxies during reionization. So Charlotte Mason briefly introduced this work yesterday. I'll go into a little bit more detail, but essentially what we're doing is using a Bayesian framework to infer the IGM neutral fraction at 2 fiducial redshifts during reionization. So we're looking at 6.7 and redshift 7.6. And the way that we did this is basically we have large samples of Lyman break galaxies at these redshift ranges, and we look at their equivalent width distribution of both Lyman alpha emitters and the upper limits from non-emitters, and we compare that distribution to a redshift where the universe was ionized or almost fully ionized at redshift 6. So the thing that we introduced in this work is we included a large sample, almost 200 Lyman break galaxies at the reference redshift of 6. And all of these were intrinsically faint galaxies. So the key here is that we're looking at lensing cluster fields, looking at lensed galaxies at high redshift so that we can actually probe typical galaxies during reionization. Our median luminosity is 0.1 L star for all of these samples. So we're able to categorize the equivalent width distribution both at faint and high redshifts, magnitudes. And what we did here is we were really able to constrain the faint end of the equivalent width distribution using our large sample of faint galaxies. So this schematic just kind of shows an overview of the whole process. So we looked at lensing cluster fields with HST, then we targeted the high redshift candidates on Keck to look for Lyman alpha spectroscopically, and then we compared those equivalent width upper limits and values at our high redshifts and our low redshifts. And to a first order approximation, we attributed all of the difference between those distributions to IgM neutrality in an evolving IgM. We also compared to forward models and inhomogeneous IgM simulations to get our final posteriors on the neutral fraction. So in the next slide, if you want to go forward, so this shows our final results. Ours are shown in orange here. So we have an upper limit on the IgM neutrality at redshift 6.7. These are all at the 1 sigma level. So the upper limit is 25% at 6.7, and then we infer a neutral fraction of 0.83 at redshift 7.6. So the implications of this are a pretty rapid and moderately late reionization scenario, implying that basically most of the reionization was done between these two redshifts, between 7.6 and 6.7. So in the future, we'd love to use JWST to expand this work, looking at higher redshifts, getting even larger spectroscopic samples in order to kind of reduce those error bars and constrain the timeline of reionization even more. Thank you.
Thank you. Roberto?
Hi. Good afternoon, evening for everybody. I'm Roberto De Carli. I'm a staff astronomer at the Observatory in Bologna. I'd like to thank the organizers for letting me present this work despite I'm still programming a supermobile. We've been talking about intensity mapping through this conference, and it's very exciting to see all this work going on. Intensity mapping is a technique that allows to reconstruct the distribution of matter and of emission from galaxies using a combination of basically the power spectrum measurement of some line emission. And the C+ line rising from the single ionized carbon atoms, that's one of the most interesting lines to observe in that respect, because it's the main coolant of the cold ISM between temperatures of, say, 10K to 1000K. And it's conveniently shifted in the millimeter band, in the 1 millimeter band of the atmosphere, so we can observe it from the ground. C+ is a workhorse for studying the ISM, the cold ISM in distant galaxies. However, as you can see from this plot, from the studies of the Labruyil and collaborators, you can see that in the Epoch of Reionization, where we would really like to use the full power of C+, the intensity mapping signal from C+ is hidden among contamination from foreground sources, in particular the CO emission, the molecular transitions from the carbon monoxide close to cosmic noon are expected to be a dominant factor. The real problem is to understand how much. Can we move to the next slide? So what we did to use the aspect survey, which is a molecular scan. We sample continuous area in the Hubble Ultra Deep Field in 3 bands: the 3 millimeter band, the 1 millimeter band, and from those big data cubes we could identify and then using the parallel wealth of ancillary data, basically any wavelength that you get in the Hubble Ultra Deep Field, we were able to identify exactly what was the redshift of all the CO emitters and all the line emitters cubes, and then proceed with a full characterization of the sources. One of the lessons we learned among the many results that are summarized in a number of papers, and I really invite everybody to visit the aspects.info website with that has lots of content with different visual data, all the data publications you'll find. One of the results was that we found that at 1 millimeter, C+ is contributing to less than 1% of all the line emission that you get in this band. This is really critical because we will be sensitive to the C+ redshift between redshift 6 and 8, and if with such a low contribution, it really becomes doing measurements of intensity mapping measurements of C+ at this redshift becomes a really delicate effort in modeling out all the foreground. The main path to do that is to get similar observation in multiple bands and try to remove CO emission by cross-correlating with different frequencies and different transitions of the CO molecule. But this is really still very uncertain because of the limited samples and the range of excitation that you can get. And with this, I'll thank you for your attention.
You. Michele?
Yeah, I'm here. Can you hear me?
Yes.
Okay, so I'm here in behalf actually of my master student, Matteo, Giulia, and Paolo, that during this month-long master project, they try to answer a very basic question, which is, can we actually accelerate radiative transfer simulation for reionization with neural networks? So basically what they wanted to do, exactly like we do from the simulation, is to predict the ionization field. So on the left, you have the ionization fraction of a large cosmological volume of about 700 megaparsec at one specific redshift, more or less, when the ionization fraction is 50%, so when the volume is 50% ionized, and this was done with a radiating transfer code, which is the C2Ray code. So the idea is to use the density distribution of the sources in the center in orange and the density distribution of the IGM on the right as input of your network, exactly like you will do for a simulation, to determine the ionization fraction. So they develop a convolutional neural network that take volume subsample of this large box and try to predict the ionization fraction of the central pixel. Here in this zoom region on the bottom right, I give an idea that why we want to predict from a sub-volume subsample the central pixel is because that they consider that the ionization fraction of the central pixel will probably depend on its environment. So depending on the number of ionizing source in its surrounding. So next slide, please. Yeah, so they, as I said, they developed this convolutional neural network that take a bunch of subsample volume of the large box, and then they try to they feed it to the network and try to estimate the ionization fraction of the central pixel. They have at the moment some preliminary results that shows here with this correlation plot on the right in blue. You have on the y-axis the prediction and x-axis the true, and they see that the reconstructed ionization field is approximately with 1 sigma error. So these results was promising enough to extend this project to an actual master thesis project of a 6-month long. And the title here in the bottom left is slightly changed in the sense that now we don't generally say neural network, but we try to see if we can accelerate the radiative transfer with a specific design network called physically informed network, which in principle are this type of network that are provided with some additional information by the, let's say, science. It's in a certain way we can provide some additional information so that we can say that the network understands the physical problem. And this is done by some implementation in the loss function on the bottom, where we add some physical motivated loss. And with that, I conclude. Thank you.
Yeah. So this brings us to the break. And first of all, I want to thank all the speakers of this session. I encourage all the participants to go to the Gather Town, and there you can find the posters for all these flash talks, and you can also talk to other participants of this meeting. You can also continue discussion on Slack. So we come back in about 15 minutes, which is at 6 p.m. UTC for the next session, where David will chair the session.
Just to say for the speakers of this session, if you want to try to see if your presentation works, you can do that now in the coffee pause.
Hey.
Hey, Thomas.
How are you?
Well.
Good. No one else seems to be testing, so I guess I'll try and share my screen.
Yeah, you can try. Yep, that works.
Seems okay.
Yeah. I cannot see your pointer, but I guess. I can. Okay.
Awesome. Okay. Cool. Thanks.
Yeah. Thanks to you. Hi, Baron. You can try if you wanna. Yep, that works. Just I don't know if you're speaking, but I cannot hear you.
Maybe he should. Hello.
Yeah, so I think now it works. Yeah.
Yeah. Thanks.
Thank you.
Hi. I'm going to test my setup as well. Can you hear me?
Yeah, I can hear you.
Okay, that's good. Can you see the shared slides?
Yeah, could you make it full screen?
They are full screen on my screen. Let me check.
I can see your browser on the top.
I clicked on full screen and full screen on my screen. Let me check again. Does it work now?
Yeah, that works perfectly.
Okay, that's good. Thanks.
Thank you.
If you need any help, David or Sambit, let me know. I'm still here.
Okay, thanks. So I see also Atridev here.
Hi, could you hear me?
I can hear you, yeah.
Okay, let me just check with my share screen thing.
Mm-hmm.
Can you see my screen?
Yes, if you could somehow make it full screen, that
Yeah,
would be perfect.
okay, let me just check. Yeah.
All right, perfect. Yeah.
Thanks.
Yeah.
Yeah, I will stop sharing.
Thanks. Yeah, I only don't see Ming Feng at the moment. I don't know if we should contact him.
Who are you looking for, David?
The second speaker, Ming Feng Hu.
Ming Feng. Oh, okay.
Um,
I can drop a quick email if she is not. Oh no, he. Sorry, he is on Slack. Should I message him quickly to ask?
yeah, you can.
Okay. Okay. Okay, let's see if he answers. Okay, he will connect. I think he's here. Oh. Okay, Ming Feng. Hi. Oh, he was. Ming Feng, can you share your screen? Sorry.
Wait a second.
Yeah. Okay. Yeah.
Is this working?
Yeah, but for the moment we see your Zoom link. So the Zoom page on your browser.
Oh no.
Okay.
Can you maybe try to share again?
Yeah, it's 6. We should restart with the talk. So I let you the place. See you later.
Yeah, we can then try later. In fact. All right. So hi to everyone. I'm David, and I will be chair for this session. We have 5 talks, and let's get started. Our first speaker is Stefan Neutsch from University of Hamburg. And Stefan, if you can share your screen, he will tell us something about inferring astrophysics and dark matter from 21 centimeter tomography.
Okay. Hi, can you hear me?
Yep.
That's good. Okay, I will be talking about inferring astrophysics and dark matter properties from 21 centimeter tomography using deep learning. In other words, I use deep neural networks to directly read out astrophysical and cosmological parameters from 21 centimeter maps of the Epoch of Reionization and cosmic dawn. To be specific, I trained the neural networks on the warm dark matter mass, the matter density parameter, the minimum virial temperature of a star-forming halos, the ionization efficiency zeta, the X-ray energy threshold for self-absorption E0, and the X-ray luminosity Lx. The simulations, the neural networks were trained on simulations which were performed with 21 centimeter fast. To get a more realistic image, we also transformed the simulations into mock images, into SKA mock images using 21 centimeter sense. And each data set, which the results will be presented from in this talk, contains 5,050 light cones. For 21 centimeter radiation from the Epoch of Reionization and cosmic dawn, the foreground contamination is expected to be wedge-shaped in K-parallel, K-perpendicular space, with the size of the wedge depending on advancements in foreground cleaning. For this talk, we look at two models. Below you can see three light cone examples, one for simulations, one for a mock model with optimistic foreground expectations, and one for mock model with moderate foreground expectations. In the optimistic case, the wedge extends to the full width of maximum of the primary beam, while in the moderate scenario, it extends slightly beyond the horizon limit. Since one of the main focuses of this talk is the warm dark matter mass, or the prediction of the warm dark matter mass, I want to quickly show how the warm dark matter mass or how warm dark matter universe influences the Epoch of Reionization cosmic dawn. And one effect is that the warm dark matter mass structure formation is delayed. We can define a Jeans mass depending on the warm dark matter mass, which is the minimum mass required for star formation. And as you can see in the top left plot, depending on the warm dark matter mass, this delays the entire Epoch of Reionization and cosmic dawn. This effect is much stronger for lower masses, and for higher masses, we get closer and closer to a cold dark matter case. A second effect or similar effect is shown on the top right, where we can see the matter power spectra for three different warm dark matter cases and a cold dark matter case. We can define the smoothing scale, at which the K mod 1 over the smoothing scale is reduced by half compared to a cold dark matter case. And yet again, we can see that the power spectrum dies down at higher mass, at larger scales for lower warm dark matter masses, and the power spectra are more similar to a cold dark matter case for higher warm dark matter masses. So before I talk about the results, I want to present the neural network architecture used for this work, since it contains two interesting features. The neural network architecture is presented at the top. The orange boxes depict convolutional layers. The darker orange boxes pooling layers. The purple boxes purple box global average pooling layers, and the blue boxes dense layers. The darker areas in the convolutional and dense boxes depict the Rayleigh activation function. So the first interesting feature for this neural network architecture is that we use a large kernel size in the first convolution of 3 times 3 times 102, with 102 being the size of the kernel in redshift direction. The idea of this is to allow the neural network to learn time dependency in redshift direction. And incidentally, this layer also reduces the input for the following layers, thus greatly reducing the training time of the neural network. The second feature is the usage of a global average pooling layer. This takes this looks at the previous convolutional layer and takes the average value over each filter. So it just reduces the nodes to just the number of filters from the previous convolutional layer. The global average pooling layer is used to reduce overfitting. As you might notice, there are no dropout or batch normalization layers in this neural network. And the reason we specifically use the global average pooling layer can be seen on the bottom right, where we can see the loss curves for training the neural network on simulations. The training loss, validation loss, and test loss after 35 epochs is very similar, meaning that we have very low overfitting. And the neural network converges very fast after 35 epochs. We are already we have already strong convergence of the neural network. The results of training the neural network on simulations are shown here, where we can see scatter plots comparing the neural network predictions and the labels or true values for 6 different parameters. And the box on the bottom right for each plot is used to compare the distributions of simulations, opmods, and modmods by calculating the difference between the predictions and the labels for each data point of all 3 cases, and plotting all 3 cases in a histogram to compare them. Since all 3 cases are fairly similar in this diagram, in most diagrams, we can assume that the neural network is fairly robust against foreground contamination and noise. The number on the top left gives the standard deviation of predictions minus labels. A smaller number means that we have a small scatter and bias for the given parameter. The parameters E0, zeta, Lx, and omega m perform fairly well, with E0 being the worst performing parameter out of the 4, but this has been seen in previous works, including both similar approaches of applying deep neural networks and more traditional approaches of applying, for example, Markov chain Monte Carlo methods. The minimum virial temperature for star-forming halos and the warm dark matter mass are a bit more difficult to predict for the neural network. For TVIR, we can see a number of predictions which are seemingly disconnected with the labels, but those predictions correlate with low warm dark matter mass values. As you might remember, when I introduced the warm dark matter, or when I explained the influence of the warm dark matter mass on the Epoch of Reionization cosmic dawn, warm dark matter, especially low warm dark matter masses, can put strong constraints on star formation, which is the same thing that the minimum virial temperature for star-forming halos does. So if the warm dark matter mass is a more stringent boundary than the TVIR, it is a lot more difficult for the neural network to predict TVIR. For the warm dark matter mass itself, we can see on the top right that predictions for higher masses are uninformative. Though for lower masses, up to maybe 3 to 4 kiloelectron volts, we get quite a good performance for the neural network. This can also be seen in the diagram on the bottom right. Note that the spike around the 0 value only appears for simulations and opmods, but for a moderate foreground scenario, it doesn't appear, meaning that we need good foreground cleaning to achieve optimal results for predicting the warm dark matter mass. In order to test the neural network architecture further, we also performed tests, or we also trained it on an astro-only data set where we assume a cold dark matter universe. Note that the minimum virial temperature for star-forming halos greatly improves without the degeneracy with the warm dark matter mass, while the other 3 parameters give very similar results. This dataset or similar dataset has been used in previous works, and the neural network is competitive with them, meaning that it might be a potential candidate for similar works. One problem that arises when dealing with mock images is that mocks might not be a perfectly accurate representation of the real data. And in order to estimate how this affects the neural network predictions, we use a fairly extreme test of transfer learning, where we first train on a neural network on simulations, and then without further training, use it to directly predict mocks with optimal foreground settings, and the other way around. In case of the X-ray heating and ionization efficiency parameters, this works surprisingly well. 2 examples are shown on the top. where we get very similar results to when we use the neural network to predict the kind of simulations or mocks that they were trained on. It's a lot more difficult when we look at parameters which influence higher redshifts, where the noise from the opmocks is a lot higher. Two examples are shown on the bottom. For the warm dark matter mass, we don't get any good predictions. For the matter density parameter, we get a very strong bias and increased scatter. The results are summarized in this table. The values in the middle are coefficients of determination for the given neural network or for the given training set, and parameter, which are calculated by the formula below, 1 minus the squared differences between true and predicted values divided by the squared differences between true and average values. The loss values on the right are given to compare the different, or the training on the different data sets as a whole. Most importantly, the difference between training on simulations and training on opmocks is pretty much negligible, while it's a bit more difficult to predict on mocks of moderate foreground settings. When comparing the simulations with the astro-only dataset, we see that for LX, E0, and zeta, the differences are negligible, though for the minimum real temperature for star-forming halos, when we introduce a degeneracy with the warm dark matter mass, predictions get much worse. For the two transfer learning cases below, we can also see that the extra luminosity, E0 and zeta, are predicted fairly well, despite basically predicting on the wrong data sets. To summarize the results, we achieve fast and accurate parameter inference with the 3D CNN. For the warm dark matter mass, we get good results for lower masses, though for higher masses, the neural network doesn't allow us to precisely determine the mass of warm dark matter. This is similar to other kinds of observations like diamond alpha observations. The 3D CNN is robust against extending the parameter space, as we've shown when training on the astro-only dataset, and when looking at robust against the noise and foreground contamination in an optimistic foreground setting. In a moderate foreground setting, the results do get slightly worse. With transfer learning, we tested the robustness against errors in the mock model. And we can see that the X-ray heating parameters and the ionization efficiency are very robust against these inaccuracies, meaning that the neural network predictions on these parameters are fairly trustworthy. Yeah, thank you for your attention. Feel free to ask any questions.
Thank you very much, Stefan. There is one question on Slack by Yima. Please, if you want to ask.
Okay. Yeah, so the question is just if you have any explanation for the large scattering in warm dark matter mass. For example, do you have some visualization that maybe shows the difference between the model cold dark matter and warm dark matter?
I mean, isn't that what I showed here? Basically, that for higher warm dark matter masses, the difference between the different models is very small. Note that the 4 kiloton volt mass, which is basically the breakpoint, is the blue line here. And from 4 kiloton volt to 10 kiloton volt, we just have the slight change. This is only when the warm dark matter mass parameter changes. When we have 5 other parameters which can do stuff, it's obviously getting harder to differ between the cases.
Yeah, but this is the global brightness temperature, and
yes,
I think the information you extract is images. So presumably there may be some other information that I don't know. Maybe that shows difference between these two different models. Yeah,
the hope is that for images we also get effects from the right plots at the smaller scales. Give some additional information.
Okay.
Okay, thank you. There are a few more questions, but we have to move on. So please start your discussion on Slack. And thank you, Stefan, once more. Our next speaker is Ming-Feng Ho from University of California. So if you can share your screen, please. And Ming-Feng will tell us something about multi-fidelity emulation for cosmological simulations.
See my slide?
Yeah, now it works.
Cool. Yeah, thank you so much. So hi, I'm Ming-Feng from UC Riverside. So I will talk about my work on multi-fidelity emulation. So this work's done in collaboration with my PhD advisor, Simeon Bird, and the collaborator in computer science, Christian Shelton. So emulators are quite popular these days. So they emerge as kind of a fancy interpolation tool, allowing us to do MCNC without running so many simulations. However, as the simulation become more realistic and complex, generating simulation data can also become increasingly more expensive. So the simulation data needed to train an accurate emulator can be difficult to generate. So for example, the Euclid Emulator 2 used more than 3,000 cube simulations to build their emulator. So this is not like the computational budget that every research group would have. So one solution to this is the multi-fidelity emulation. So you can imagine we can run many low-fidelity simulations with low resolution, but can be performed quickly and cheaply, and combine them with a few high-resolution simulations. And we use both low and high fidelity data to predict the high fidelity outputs. So the goal of this talk is to show that multi-fidelity emulation is a useful thing to be adopted in your emulation pipeline. And another thing is that it's very easy to train compared to neural net. So one analogy I really like is that in academia, you can imagine professors are the most high fidelity researchers, but the university won't be able to hire so many professors to do research. So the solution here is to hire as many graduate student researchers as possible. So students do the hard work exploring different research topics, and we only need a few professors to calibrate the students' results. So in this way, university can achieve both efficiency and accuracy. Here I kind of summarize the workflow difference between the single fidelity one emulator and the multi-fidelity emulation. So I will start with expanding the single fidelity one. So the first step is the experimental design, which you choose the optimal points in the prior volume of the parameter space, usually a space fitting design using the Optical hypercube. And then you run the simulation suite based on those points, and then extract the quantity of interest. For example, in our case, it's the meta-power spectrum. And then you build an emulator using statistical modeling tools like the interpolation tools or a Gaussian process. And for the testing part, you need to validate the emulator accuracy. The errors need to be lower than the observational error. And after the testing is done, you do the inference, apply the emulator on the input observations. So for the multi-fidelity emulation, we again start with the experimental design, but this time we start with the low fidelity one, which is again a space fitting design. However, for the high fidelity, we can use the low fidelity data as a prior to optimize the choice of high fidelity simulations. That is, we find the points that give the best interpolation results in the prior volume. And then we extract the quantitative interest again from both low fidelity and high fidelity. Using this training data, we put into the statistical modeling framework, for example, Gaussian process and the KO method, which I will explain later. And the testing and inference steps are the same as the single fidelity one. So here is the experimental design we use in our previous paper. And for the multi-fidelity simulation, the experimental design will be a nested experimental design. And this is only, so our paper is only, previous paper is only working on the matter power spectrum from dark vector only simulations. So the low fidelity one is the space fitting strategy. And these are the 128 cube simulation in 256 bucks. So in the plot, they show us blue dots there. For high fidelity, they have to be a subset of the low fidelity rounds. So they are 512 cubes simulations in 256 bucks, showing 3 orange dots in the plot. So what we are trying to do here is to improve the resolution by 64 with only a few high resolution simulation rounds. And here I explain the statistical modeling tools we use. So the most popular multifidelity method is the KO method, the Kennedy-O'Hagan method, which is developed in 2000. So KO method models a sequence of simulations from the lowest to the highest fidelity using a linear autoregressive framework. So on the left-hand side, you can see this is the output from high fidelity we want to model. On the right-hand side, you have the output from low fidelity multiplied with a scale parameter plus a bias function. The low fidelity function is a Gaussian process, and also the bias function is a Gaussian process. And it is proof that you can train the KO method recursively. That is, you can train the low fidelity Gaussian process first, fix that, sample the posterior from that, and train in the high fidelity one recursively. And for the NARGP, the non-linear autoregressive Gaussian process, this is an improved KO method by modeling the scale vector as a Gaussian process kernel. So here are the testing results from our multifidelity emulation. So in the plot, the y-axis is the relative errors, and the x-axis is the k-modes from matter power spectrum. So if the relative error closer to 0, it means the emulation is good. From the top left, single fidelity emulator with 3 high fidelity simulations in orange has a poor performance as expected. But if we increase the number of simulations, then the maximum error kind of improve like to 5%. On the other hand, if you use multifidelity emulation, you get a much better performance by only use 3 high fidelity simulations and 50 low resolution simulations, which is shown in blue lines here. But you might wonder, what's the computational budget for all of these? So here is the plot that summarizes the computational budget versus the emulation error. So for the low fidelity only emulator, this is single fidelity, but only trained on low fidelity data. It doesn't change much due to it already kind of achieved a good interpolation with 50 initial samples. For the high fidelity only emulator, that the error is large when you have only a few samples, but the error decreases with more and more simulations. But you will notice that the error, when the error is going down, that it's getting harder and harder to decrease the error with more simulations. And compared to the multi-fidelity emulation here, you can see that the multi-fidelity emulation gets the kind of the same level of accuracy with the high fidelity one with lots of samples, but it's much lower computational budget here.
5 more minutes.
Oh, thank you. And you don't have to be limited by our design. The multi-fidelity emulation is very versatile. You can increase the resolution of low fidelity round, and then improve the emulation accuracy, and you can downgrade the low fidelity to save more computational budget but sacrifice some accuracy. So how to design an optimal multi-fidelity emulation? It depends on the error you are aiming to achieve and the total budget you have. So here is the conclusion. First, I've shown that you can save the budget without losing imaging accuracy by using multi-fidelity design. And it can be applied to existing simulation suite, since people usually run their simulation in several different resolutions. And also, you can imagine you can triply increase the dynamic range of simulations using multi-fidelity. You don't have to run many large box high-resolution simulations to build your emulator. You can just run a bunch of large box low-resolution simulations, pairing them with a few high-resolution runs to calibrate the result. That's it. Thank you.
Thank you very much. Do we have some questions? I have several ones. So I'm not expert in this method. I was wondering. So is the box? So I saw that the box size has to be the same in both high and low fidelity. Is that necessary? Could the method be developed by, for example, taking the smaller box size for higher fidelity simulation?
Thank you. This is a very good question. That's something we are exploring right now. So you don't need to fix the box size actually, we have tested that you can actually change the box size for low fidelity. You can like have a smaller one or large one, but usually the same box size will work best. But in some other multi-fidelity design, like there's a new method proposed last year that you can have different numbers of low fidelity simulations. You can imagine you can have different box size for low fidelity, but predicting a fixed box size for high fidelity. And yeah, so the answer is that you don't need to fix the box size actually.
All right. Yeah. I mean, that could reduce the cost of computations significantly, right? All right. Thank you. There is one more question by Galt. If you can.
Yeah, thanks. So very interesting approach. I didn't really get, what are you emulating in your example?
Yeah, so we are emulating the meta-power spectrum from the unbodied simulation.
But that's the input, right?
The input is the lambda CDM cosmological parameter. Let me switch to that slide. And we have, I didn't show the prior volume here, but we have fairly wide prior applying on five parameters here.
So you're trying to emulate the nonlinear matter power spectrum after, right? Okay.
Yeah. Thank you.
Yeah.
Thank you very much. For all other questions, please post in Slack, and let's move on to the next speaker, Baron Meiti. If you can screen.
Am I audible? Hello.
Yep.
Am I audible?
Yep.
Yeah, let me share my screen. So is my screen visible?
Yes, just if you can go full screen. Yep.
Yeah. Yeah. So hi, I'm Baron Meiti from NCRA TIFR. So first of all, I'd like to thank the organizers for giving me the opportunity to present our recent work. So I will be talking about efficient modeling of cosmic reionization using script. So I'd like to start with a brief motivations behind this work. So as we know that reionization is still one of the least understood phases in the evolution history of the universe. So there are a lot of uncertainties like the precise reionization end, the duration of reionization, and we don't even know what are the nature of the ionizing sources. So the advantage we have that there are a bunch of observational probes in different wavelength bands. So ideally, one would expect to combine all these probes, if possible, simultaneously to extract the information about reionization. And we know that there are quite a few upcoming observational facilities which will be targeting to explore the reionization era. Thirdly, we'd also like to check the prospects of thermal history of the IGM as its treasure of reionization. And in literature, there are a lot of studies which have already proposed this, but probably this is one of the less explored areas in the community. So we would like to take a look at this too. And lastly, as we know that there are a lot of uncertain astrophysical parameters during those high-redshift. So one has to have an efficient model in order to get constraints on defined uncertain astrophysical parameters and correctly infer the observational data. Now let's move to the script. So script is basically one of these fast semi-numerical models. It stands for semi-numerical code for reionization with photon conservation. So as the name suggests, that it basically solves the problem of photon number non-conservation, which is generally associated with semi-numerical models based on excursion set approach. So the non-conservation of photon number, it has some further consequences, like it produces non-convergent 21 centimeter power spectra at large scale. So whatever small scale physics you include in your simulation, the overall large scale features should be intact, because this is going to be an observational probe in near future. So script solves that problem. And in this particular study, we have modeled these three physical processes during reionization. So the first one is the thermal evaluation of IGM. So we know that the ionizing photons not only ionizes the medium, it also heats up the medium. So we need to model that. And in order to model that, we basically need to solve this standard temperature evolution equation for each of the cell in our simulation box. And to model the reionization heating, we need to introduce a parameter which basically gives the temperature increment for a region due to the full ionization. So this is a free parameter in our model. The second one is the inhomogeneous recombination. This is also well known. So we need to track the density evolution and the ionization history for each of the cell in order to compute the recombination number density and tune the ionization criteria accordingly. And for the inhomogeneous recombination, we have to have some parameter which basically quantifies the inhomogeneities in the medium. And this is given by this free parameter, commonly known as clumping factor. In our case, it is a global parameter which can be a constant or can be a redshift dependent. And the third one is the radiative feedback. It's basically a consequence of reionization heating. So there will be inefficient star formation in lower mass halos due to that excess radiation pressure. And in generally, it is modeled with a minimum threshold mass, which is temperature dependent, and the suppression may be step-like or maybe gradual, depending on the case. So let's move straight to some of the results. So in this plot, we have shown the reionization light cones for three different cases. In the fiducial cases, we have both recombination and feedback effect. And in the middle panel, we do not have any feedback effect. And at the bottom, we neither have recombination nor have feedback. So clearly, we can check that reionization is delayed if we include the recombination and feedback. And this has been in similar notes with the other studies using different semi-numerical models. And for all the three cases, we have basically fixed same ionizing efficiency factor, which is needed for any kind of semi-numerical reionization model. Next, we plot the temperature light cones and find that it basically traces the ionization field quite well. And this is important in order to model the radiative feedback. But if we want to get a direct observational probe, this is not so useful. Instead, which is useful is to estimate the temperature of low density IGM. So from the full radiative full hydrodynamic simulation, it has been shown that the low density IGM temperature follows a power law with the overdensity, and we try to model it using subgrid physics, And we find that we basically get similar kind of trends which has been suggested by the full simulation. So as reionization proceeds, we can get a nice correlation with the temperature and the overdensity. And this color bar is basically showing the redshift, the ionization redshift for different cells. So the scatter is basically due to that different regions in the universe is ionizing at different redshift. And similarly, we have shown the plots for 3 different models, and we find that if we do not include recombination, the correlation is not so stronger. So recombination is actually an important part. And now what we can do, we just fit a straight line through this and try to estimate this normalization T naught, that is the temperature mean density, and this power law index gamma. And we already have some estimates of this temperature and the power law index around redshift 5 and 6. So in principle, we can use this as a potential probe of late phase of reionization. So we have plotted a variety of models, basically by tuning different parameters in our model suite. Like we have for a fiducial model, we have taken a clumping factor of 3 and TRE of 20,000 Kelvin, and for we can tune it to a high clumping factor of 5 or high temperature increment parameter. So what we find that very extreme models can already be ruled out by the available observation constraints. So yes, it can be an important probe for the reionization. The next one is the pretty well-known one, the UV luminosity function. It basically gives an estimate of number densities of the galaxies per unit magnitude bin. And we find that radiative feedback suppresses the faint ends of UV luminosity function. So this cyan line does not contain any feedback effect, but if we include the feedback in this, say, this blue line, we see this there is a suppression. And right now the uncertainties in the data are much larger, but in future with the help of telescopes like JWST, we should be able to reduce these uncertainties and the model degeneracies can be broken. And for modeling the UV luminosity function, we have to have another parameter, which is the escape fraction, and that we take as a mass dependent fiducial form. So in principle, we can also tune that parameter to get a different value for UV luminosity function. And the next one is the most promising one in this field, that the 21 centimeter power spectra. So it basically traces the fluctuation in the neutral hydrogen field and carries the imprints of very fast sources. And we have plotted the power spectra at K value of 0.08 H by moving megaparsec. And at the top panel, we have shown the plots, shown the variation with redshift, and at the bottom panel, we have shown it with the mass average ionization fraction. And what we find that if we include recombination and feedback, the amplitude of the power spectra is suppressed. So this is important to take into account. And with the upcoming telescope like SK, we should be able to pin down this power spectra within 10% uncertainty. So this is important to take into account all these effects. Now let's move to the most profound parts of any kind of fast semi-numerical models, that we are able to do full parameter space exploration with the available observational constants. So in our case, we have basically 5 free parameters. So we can define the ionizing efficiency with a redshift dependent form, where zeta naught is the normalization and alpha gives the power law index. Similarly, we model the escape fraction as a mass dependent form, and this if escape naught is the normalization, and beta gives the power law index on mass. And we have that reionization increment, the reionization temperature increment parameter TRE. And these are the observational constraints which we can use, that we have model independent limits on ionization fraction from the dark pixel studies. We also have the CMB scattering optical depth from Planck, and we in our model, we have the privilege to use this IgM temperature estimates at the low density IgM, So we also use that, and we have used UV luminosity functions at redshift 6 and 7. And we also put a card that Reionization is aimed by Z redshift 5.3, which has been shown some recent studies. So these are the basically posteriors of our analysis. So these the first 5 are the free parameters in our model, and the last 4 are the derived parameters. So the delta Z is the Reionization interval, as we can say. It's basically the redshift interval between which the medium goes from 25% to 75% ionization state. Z mid is the midpoint of the ionization, and this Z75 is when the medium is 75% ionized. So in this plot, we have basically compared what the effects on the parameter spaces if we include the temperature data and if we do not include the temperature data. So clearly it can be seen that our parameter TRE is well constrained with the low density IgM temperature estimates. And not only that, it also improves the bounds on the other parameters too. Like if we take a look at this Z75, we found that the constraints are much more stringent if we include the temperature constraints. And this is the plots for 200 random samples in our MCMC chains. And the top panel, we have shown the reionization history. And as I was telling that if we include the temperature data, the very early reionization end is not preferable, which is in line with some of the recent findings. And at the middle panel, we have shown the plots for the temperature at mean density, and we found that this temperature is well constrained with the available observations. There are a lot of models which are discarded if we include these constraints. And we also lastly check what's the effect of feedback on our parameter spaces.
2 minutes.
So yeah, I'll be done. So we find that if we do not include feedback, there is a strong degeneracy between the Z75 and this reionization temperature increment parameter. But if we include the feedback, the degeneracies can be broken. And as we can see that the feedback also prefers late reionization end and a slightly longer reionization duration. So to summarize the work, so we have modeled the effect of inhomogeneous recombination using fully photon conserving code script, and we also probed the thermal immunization of IgM, which is necessary to model feedback, and we checked the effects on a variety of observables, and we found that we can actually use low density temperature estimates as an observation probe of reionization, which has not been studied much earlier. And lastly, we also pursue a full parameter space exploration with these models and available observation constants. The parameters are reasonably well constrained, and this will improve with more observational data, which will be coming in near future. So thanks. I would like to stop here. If there are any questions.
Thank you very much, Varun. Unfortunately, we are out of time, so please, if you can ask the questions to the speaker in Slack. Thank you once more. And our next speaker is Atridep, if I say it correctly. If you can share your screen. Atridep will talk.
Just give me a minute. It's some problem. So just give me a minute. Can you see my screen now?
If you can just
Hi everyone. I would first like to thank the organizer for giving me the opportunity to present my work. So I will be talking about parameter estimation package which I was developing with collaboration with Tirthankar Raichodhuri and Saurabh Mitra. And the basic goal of this parameter estimation package is to constrain the cosmological and astrophysical parameter using high redshift observations like Re-Ionization related observation and cosmic dawn observations. So as we all know that the Cmb photons that come from the epoch of recombination, they usually interact with the free electrons that are generated at the time of reionization, and the interaction is imprinted in the Cmb angular power spectrum observations. And given these observations, and if we assume some kind of a reionization history, one can actually compute the Thomson scattering optical depth tau. And once you calculate this optical depth, it has become a customary that whenever one proposes a reionization model, then they calculate the tau from their reionization model and then compare the tau coming from their reionization model with that of the Planck derived tau. However, there is a caveat. The caveat is that when Planck uses the value of tau that Planck quoted is usually use a tan hyperbolic model for reionization, whereas the reionization model will give a more physically motivated. So the problem is that the comparison is not fair because tau in principle depends on the reionization history that one uses. So the way to overcome this problem is that you can connect your reionization model with a Cmb anisotropic code like CAMP or class, and then can constrain cosmological and astrophysical parameters simultaneously. And also note that you would always like to vary cosmological and astrophysical parameters simultaneously. Otherwise, there could be some degeneracies between them. Okay, so far is the case for reionization. Now let's look what 21 centimeter signal can tell us about constraining parameters. So I have tried to put a figure here where the y-axis is basically the brightness temperature and x-axis the redshift. Now look at this two brightness temperature. So what I have done is that we kept all the other model parameter fixed, be it cosmological, be it astrophysical, and put one with with a larger value of sigma 8 and one with a smaller value of sigma 8. And you can see that when I use a larger value of sigma 8, which basically translates to earlier structure formation, the depth is more like minus 500 millikelvin. Whereas the moment we lower the value of sigma 8, the structure formation takes place at a later redshift and also obviously takes place at a lower depth as well. So we see that there is some effect that is going in the 21 centimeter signal, which depends on the cosmological parameter or the astrophysical parameter that we will use in our model. So to this aim, we have developed a pipeline called Cosmo Re-Ionization, which is written completely in Python. So in this cartoon, I tried to give a block-wise presentation of the whole code. So what we have done here is that there are three theoretical models. One is the 21 centimeter model, and another is Reionization model, and one is the CAMP model, which basically gives you the CLs. And the Reionization model give you observables, which are, in our case, they are the Lyman limit redshift distribution and the photoionization rate. And the 21 centimeter model gives you the brightness temperature. And in case of the observational data that we will use to make the comparison with our theoretical model, for the CL we use the Planck 2018 data. For the quasar observations, we use, I have already mentioned the Lyman limit and the gamma pi data, the photoionization data. But note that at the time of 21 centimeter data, we are not using ages data. And this is one of the reasons is that recently Saras, another collaboration, has published a paper which basically says that the 21 centimeter data that the ages people have found, they have rejected that detections at a 95% level. So right now you will be using a mock 21 centimeter data, and we will see the potential of 21 centimeter data to put constraint on the cosmological or the astrophysical parameter that has been used. And we use a publicly available MCMC package, which is called EMCE. So basically what we do is that once we produce the theoretical values of all these observables, we compare them, compute the chi-square, and run an autocorrelation analysis to check whether the run converges or not. If it does, then we do some post-processing to get the result. And if it does not, Then we basically take the same, then we basically again change the different parameter values. And the different parameter value means here the cosmological parameter, which is given by this theta cosmo, the Reionization theta Re, and the 21 centimeter signal theta 21. So as you can see, our parameter space is 9-dimensional, I believe. So the cosmological parameters are H0, the Hubble, all the known parameters, and this is the Reionization parameter, which is basically the escape fraction, and this lambda 0 is a free parameter which is associated with the mean free path of the ionizing photons. And fxh and f alpha are two free parameters which are used in 21 centimeter modeling. This basically f alpha computes the Lyman alpha efficiency parameter, which is an important parameter to which we need to use at the time of 21 centimeter modeling. And this fxh is basically the heating efficiency of the X-ray photons that are coming out of different sources. So these are our free parameters, and we have to keep one parameter fixed, which is the star formation efficiency, which is given by 0.01, which we fix by comparing with the UV luminosity function data. And the time of likelihood, we use a likelihood which is basically the summation of all kinds of observable data that we are using. So LPL is the Planck, LRE is coming from the Reionization, and L21 is what I have already described. And on top of that, we put two priors. So one is that the Reionization must be completed at Z around 5.3. We make sure that there will not be any model in which the Reionization is as late as this. And also we put the limit on a neutral hydrogen fraction limit, which comes from the dark fractions in quasar spectra. So let's first check whether our MCMC chain gives you a result which is comparable with the observations. And you can see that the Reionization observable, which is the Lyman limit distribution and the photoionization, you can see that these black points are the observational data, whereas the best fit parameter, which is basically the blue one, you can see that it closely mimics the observations. So you can see that this part is at least fine. And next, when we talk about this 21 centimeter hypothetical data, these black data points are these hypothetical, whereas this magenta color basically shows you the best fit. And you can see that it closely follows the mock data. So you can see that the MCMC chain runs well. And now we will come to the result part, which talks about the constraint on cosmological parameter. So you see in the red color, we put a constraint that comes if you use a CMB and the quasars, that is the Reionization related observations. Whereas this magenta color shows you when we use the 21 centimeter mock data along with this. And now the moment we use this extra global signal, you can see that the constraints are now becoming more tighter. For example, you can see in case of this AS, or say for example sigma 8, or most prominently at tau, you can actually see that the effect of global 21 centimeter signal does actually shrink the constraint. Okay, so that will bring us to our summary, which is that, so we first mentioned that that the tau that the Planck give you is based on a tan hyperbolic reionization. Whereas when one theoretically estimates tau from their reionization model, it basically, they are from two different reionization model, and comparing them is not a correct approach. So the remedy is to connect the reionization model with CMB anisotropic code like CAM or class, and then we introduce a parameter estimation package called Cosmo Rein MC, where we connect the reionization model with CAM and vary both cosmological and model parameters simultaneously to put constraint on them. And also for the first time, we include we want to see the potential of global 21 centimeter signal to put tighter constraint on cosmological parameters. And indeed, we found that the moment we include global signal data, and it actually puts significantly tighter constraint on different cosmological parameters. Thank you.
Thank you very much. Are there any questions for the speaker? So I may have one. Sorry, there is one hand. Stephen, please.
Hi, yeah, thanks for the good talk. I just wanted to ask, have you considered, so when you consider the global signal, global 21 centimeter signal, we don't usually just have, an estimated global signal. We have something, we have foregrounds in there as well, which we have to remove, and they typically get correlated with the signal parameters. Have you checked how much that degrades performance?
No, we did not consider any kind of foreground here. We just assume that the global signal will somewhat look like this, and as if there is no foreground. We did not consider any foreground effect at all.
Okay, thanks.
Thanks, Sambit.
Hey, when I talk, I just wanted to ask about the mock 21 centimeter observations that you use, the mock values that you chose for your cosmology. So for CMB, you used real data, or were they also mock?
No, the mock part is only the global 21 centimeter signal. All the others data are real data.
Right. Okay. But for your mock 21 centimeter data, what cosmology did you choose?
Okay. So for cosmology, we vary all the cosmological parameters. You can see all
no,
these
but
NAs.
for the mock, you have to choose a cosmology.
Oh, okay. Okay. That's the Planck 2018 best fit data.
Okay, so you have chosen the center of.
Yes, that's true.
Okay.
Yeah.
Okay, thanks a lot. If there are no more questions, then thank you once more, and let's move on to our last speaker of today, Thomas Bini from Tsinghua University. If you can share.
Hello. Can you hear me?
Yeah, we can hear you.
Okay. Hi, I'm Tom Binney. Thanks for the introduction, David. I finished my PhD last year at Imperial College, and I started a postdoc at Tsinghua Uni in Beijing. And I've been mainly working on statistical analysis techniques for both the EoR and the cosmic dawn. And thanks to the organizers for letting me present my work. Okay, so I'm going to apologize a little bit in advance for going quite quickly over some of the parameters that go into these EoR models, just to focus on the statistics. But I'll try and allude to the astrophysics specifics that they are distinguishing. But this will be an overview of some research that I published midway through my PhD and some work that's due to come out quite soon. And then looking at how to improve this technique, how to improve these techniques using statistics, as well as some work that's slightly different, but uses the 21 centimeter signal to help analyze large astrophysics surveys and probe some quite sensitive techniques in the cosmic dawn. So to start with, I'm going to give an overview of Bayesian model selection. So the key to this is that we want a quantity called the evidence, Z, and this is a probability of a data set given a model. So for different models in the same data set, we can calculate lots of these Zs and then take a ratio called the Bayes factor B here, and that gives us an odds on which model is more likely. And throughout this work, we calculate this Z using multi-nest, and all of the 21 centimeter simulations are calculated with 21 centimeter fast, and telescope noise is 21 centimeter sense. So to get this evidence, we need a likelihood, and this evidence is actually an integral over the likelihood. And conventionally, these are defined with chi-squares, and throughout this, for the 21 centimeter work, we use a spherically averaged 21 centimeter brightness temperature power spectrum. So the technique works by, to test the technique, we generate a mock data set with some fiducial parameters, and then we are essentially trying to get out what we get back in. So pretty much everything in this talk uses that hypothesis. So just to highlight the published work, so we have been able to distinguish different morphologies and scales of reionization, where so inside out and outside in being whether reionization starts correlated or anti-correlated with the density field, and local being a pixel by pixel implementation versus global being an excursion set formalism approach. But crucially here, these toy models of the EoR produce vastly different 21 centimeter power spectrums, which enables 21 centimeter observations to distinguish them, while other techniques can't because their reionization histories are similar. So here are the money plots from that paper where using 21 centimeter sense, we can estimate that with about 300 hours of observations, we can get a conclusive conclusion with SKA data. So now moving on to more astrophysical models, we then iterated this technique in introducing things like the epoch of heating and X-ray parameters, as well as luminosity functions. And the same can be said for the post-heating approximation. So these plots have now converged, although there's a few left in the paper that's soon to be released. Although crucially, it depends massively on the parameters that actually are the realization for the X-ray heating. So because X-ray heating parameters can fit back down to the 21 centimeter power spectrum, there is a chance that it may be difficult to distinguish those. But in the cases that we looked at, it was very easily distinguishable. However, with just the 21 centimeter power spectrum, a power law in halo mass for the ionizing efficiency could not be distinguished. But including synergy with luminosity function data allowed distinguishing of that, as well as a second power law for the fraction of mass in stars. So I know I've gone through that quite quickly, but crucially, we should be able to tell apart morphologies. The spin temperature should be distinguished, and synergy is really crucial. However, these have been really, really slow, and there's a lot of information that gets thrown away in the formation of the likelihood that gets calculated. So if we look at the information side of things first, we have been developing the Morley transform, which this paper by Cathtrop shows this working really, really well on toy models. And in brief, we replaced the Fourier basis within the power spectrum with a Gaussian envelope that adjusts itself along the line of sight to adapt to the evolution of to adapt to the light cone effect. While previously we had to split up the light cone into chunks to get an ergodic statistic, we should be able to analyze the whole light cone at once, getting access to larger modes. So trying to interpret this, we simulated 5 sets of parameters, and it's clear that more signal comes from early in reionization, which seems good. And there is sort of a similar behavior to a power spectrum, and lots of detail that can be learnt from it here. However, there's a caveat in that because this statistic evolves along the light cone, the covariance changes along the light cone. And so where previously the peak finding exercise of parameter estimation could omit a covariance matrix, we now need to include it to help weight which parts of the wavelets are crucial. And calculating this with 1,000 realizations of different at different random seeds, we can see that it changes depending on the parameter choices as well, quite significantly. So it seems unclear to me at the moment, or to us at the moment, whether this will affect this likelihood significantly to the point where we perhaps need to calculate 1,000 realizations to do an MCMC, which would be sort of, which would be pretty undoable. However, if we load in the one calculated for the fiducial parameter set used to create the mock data, it improves things quite drastically. So on the left-hand side, we expect a Fourier power spectrum to be bad, as the whole light cone is analyzed at once and the statistic is not very ergodic, while the Morley power spectrum then has access to the large scale modes. While if we chunk up the light cone, the Fourier power spectrum becomes closer to ergodic, while the Morley power spectrum loses access to the large scale modes, and the wavelets are effectively filtering out the data and it loses quality. However, a lot more covariance analysis needs to be done, and this is quite preliminary at the moment, and we need to include telescope noise. So turning to the speeding up side of things, we've been looking at applying neural networks to model selection problems. And I've been working in collaboration with Xiaoxing Zhao, who's giving a talk early tomorrow for me. So if it corresponds to your time zone, please check that talk out. But I've been playing with PyDelphi, and which removes from using a chi-squared type likelihood to looking directly at the information content contained within the light cone, and doing so by using the neural network to compress that data, and then relating, instead of a probability, we're sort of looking at an information content, since these two things are intrinsically related. There is potentially some model selection analogies like there are with regular likelihoods. So to test this, we started looking at the model that Alsing et al. Tested PyDelphi with. And to start with, multi-nest agrees with PyDelphi, which is always a good thing. And then I've invented a bad and a good model, where the good model is the model you'd expect for cosmological parameters. And then I've just sort of randomly moved these, but random apart from the Hubble tension one, which I couldn't resist. And we are able to get out what we put in, where the good model is favored significantly, and the bad model, which is made bad by these parameters in the square bracket being fixed with delta functions on the wrong parameters, has a significantly smaller odds ratio, and this odds ratio is actually very, very similar to the change in parameter space that's been inputted by these delta functions. So now onto this survey exercise, I need to introduce the velocity-induced acoustic oscillations in the cosmic dawn. Now these will be what for the BAO did for the CMB community. Hopefully these will be the VAO for the 21 centimeter community, and will be just as revolutionary, if not more, particularly on helping analyze large surveys. So at the end of recombination, there is a big pressure change that causes sound waves in the early universe, and these imprint themselves on the formations of galaxies. But crucially, no other error has a level of sensitivity to whether things dip in and out of these potential worlds. So this is quite an interesting error for analyzing niche effects. So how do we actually try and do it? And that's by simulating lots of boxes of different redshifts, and then fitting a polynomial to the part of the power spectrum with no wiggles, the linear part, and then including this VAO, and that is fit with 6 parameters. But then we also resimulate changing some small effect, which I haven't specified yet, and we label this with an amplitude and try and work out how much that changes. And then calculating Fisher matrices within each of these boxes, we can then use those boxes themselves as pixels or voxels within a larger volume space. And again, using a Fisher analysis to combine the local Fisher analyses into a global error.
5 minutes.
Okay. So now applying it to an example. Salim Hortinley is a fellow at Johns Hopkins Uni, and we did our PhDs sat next to each other at Imperial, and we spent he did his on CMB analyses and inflation mainly, and we talked a lot about trying to probe the early universe with 21 centimeter and how we can get these statistical analysis techniques to work. Well, he has introduced me to compensated isocurvature perturbations, what I really understand by this is that we can test multi-field inflation using this criteria of a compensated density fluctuation between baryons and cold dark matter that has this specific relationship. And it is hard to measure with conventional techniques like the variance of the CMB and looking at the higher order terms in matter and matter power spectrum and the BAOs. So here we've got the green part is the linear of the power spectrum, and then the blue bit being the total, where these wiggles being the velocity induced oscillations. Now, including this CIP, which is dictated by these equations, we can re-simulate this box and work out the shift in the VAO. So by simulating 5 large boxes at various different redshifts, we can then fit the cosmology using the polynomial I showed you a few slides ago. And we can take advantage of these teeny tiny effects being amplified massively by the VAOs. So here you've got a function of the error on this effect, the CIP amplitude, and the survey volume. And you can see in certain cases where if we get blocky with baryonic feedback and we end up with an optimistic 20 centimeter observation, some of these observations, this technique can be up to a factor of 10 more constraining than other conventional techniques used in this field. Okay, how am I doing for time? Just quickly to summarize. Model selection is being done. Morphology should be done with a detection. The epoch of heating will be detected depending on the realization. The synergy is necessary to pin down power laws and halo mass for ionizing efficiency. The UV luminosity function data is particularly good at doing this. The Morley spectrum is an ergodic statistic and looks good at adapting to analyze the light cone. And model selection should be sped up significantly with neural networks, subject to some more analysis and collaboration with Xiaoxing Zhao. And there's an exciting time to be looking at early universe physics with the developments of things like the VAOs. Okay, thanks.
Thanks a lot, Thomas, for a very nice talk. Are there any questions? So I have a few.
Yeah, please.
So I didn't understand for this Morley transform. Then actually what you do is that you use this specific function in the redshift direction, but in the sky plane you actually use Fourier transform, and then you average on a sphere of a combination of the two.
Sorry, could you say that again, please?
So do you use this function only in the redshift direction, but then in the sky plane you actually use just pure Fourier transform, and then you average over the whatever is the sphere in this space.
So it's centered along a certain point in the line of sight, and then the Fourier basis across all directions is averaged here, and then we end up at a given k perpendicular with this wavelet that depends on each parallel mode given a point, a central point for the wavelet.
Okay, I understand. So actually it's just cylindrical average in the sky plane.
Yeah.
All right. And have you tried, for example, then in the pipeline to use, let's say, just 10 realizations to calculate covariance matrix because this would be more or less enough. It would be order of magnitude harder to compute, but maybe it would be feasible.
No, I haven't. That sounds interesting. Yeah, I'm quite keen to hear more about that.
All right. Some other questions? If not, then thanks, Thomas, and we can continue discussion on Slack. Well, that's really it for today's talks. And let me remind you that the next session starts at 4 a.m. UTC. So everyone who is available or awake, please join us. And that's it. Join also GatherTown to see our flash talks and posters there. And that's all from me. Sambit?
Yes, we have made all the announcements, and we'll have the final 2 sessions of day 3 at the same time, starting at the same time as today, which is 4.
Yeah,
PM
session 3 and 4
UTC.
will be at 4 p.m. UTC time. So yeah, we will have 2 sessions, one in, say, Pacific Asia, and the last third and fourth session will be more Europe and USA oriented at 4 p.m. UTC time.
All right, then I guess that's it. With announcement,